So, good morning, everyone. You made the way back here. All right, that's great. We got a full packed program today, so we'll start right away. And there's 3 paper sessions actually coming up today. The most important part is also lunch, and the boat tour, and more. And there's a small opening remark I want to make. And in case you've been at HPG or like registered for HPG last year, there was the option to collect or to get a wooden canal box, right? And Andrew has been working overtime whole year, and he cannot see the canal box anymore because he had to make so much of them, so he wants to get rid of them. So please, if you still owe one, please go down to the registration desk today and pick it up, so he actually can do something else for a change. Right, so getting into the paper sessions, we have 4 great papers coming up. It's on appearance and modeling. And the first paper is presented by Thomas Deliot, and it's on real-time rendering of Glinty appearances. So have fun.
Thanks. All right. Hello, everyone. Don't have sound. Is it fine with sound? Today I'm going to talk about real-time rendering of Glinty appearances. But first off, what are glints exactly? I've selected a few examples here. Glints come from a distribution of very specular microfacets on a surface, and it is a mesoscopic phenomenon, something that happens in between the microscopic and the macroscopic. In this work, we bring needed improvements on key areas of real-time glint rendering, and the question we asked ourselves was, what do we need to do for games to finally start using this stuff? And so we built our entire project with this in mind. So as I was saying, glints happen in between the microscopic and the macroscopic scale. The microscopic here is on the left. It's when we can see the individual microfacets on the surface. The macroscopic is on the right. It's when we zoom out far enough for the individual orientations of the microfacets to converge. And the mesoscopic is in the middle, when we can't see the microfacets anymore, but their individual orientations are still statistically important in the result. In rendering, the microscopic is typically handled by a normal map, and the macroscopic by a continuous BRDF model, thanks to the NDF, the normal distribution function. But what can we use for the mesoscopic scale? In the world of offline rendering, we can use the method of Jacob and others. This paper's contribution is a mesoscopic microfacet model, which is both simple and able to reproduce the effect of glints with a strong spatial and angular variation. Because glints can be summarized like this visually. It's a variation of the reflectance along the surface, as we see in the picture, but also a variation in movement when the camera or the light moves. Their method simulates a distribution of a finite number of microfacets on the surface, each with a 2D position and a 2D orientation, and they replace the NDF by a counting process in those 4 dimensions. For a given pixel footprint, they go through all the microfacets and count how many fall within it. And among them, they count how many reflect the incident light towards the camera. And in this model, the microfacet's reflectance is binary. Either it reflects light in the right direction or not at all. This counting process aims at computing the ratio between the amount of reflecting microfacets and the total amount. And roughly speaking, it's with this that they can replace the continuous NDF. It gives them a stochastic NDF instead, which depends on the position of the pixel footprint. But to evaluate it, they need to explicitly go through every microfacet of the predefined distribution. That's a very expensive 4D search, and thus this method is reserved for offline rendering. So let's talk about real-time now. There are a few methods which aim at offering a real-time mesoscopic microfacet model, both physically based and sticking to the constraints of real-time rendering. And the method of Zur and Kappinen here just happens to be an approximation of Jacob's method we just saw. So how did they manage that? With a few clever compromises. First, they chose to constrain the spatial distribution of the microfacets within a grid with only 1 microfacet per cell, and this allows counting the amount of facets within the footprint analytically. It's simply proportional to the area of the footprint on the surface and the microfacet density parameter. And secondly, they chose to free themselves of a unique microfacet distribution predefined on the entire surface and for all possible viewpoints. Instead, they decide to assign a random number theta to each pixel footprint P, and to define for this footprint its own procedural distribution of microfacet orientations. And finally, they chose to keep the binary microfacet from Jacob's model, which are either reflective, either not. And thanks to this, they are able to directly evaluate the amount of reflecting facets with a binomial law. And for n Bernoulli trials with a probability p of reflecting light. More recently, we also have the paper from Shermain and others. They based their method on the same compromises as that of Zur and Kaplinen to also target real-time performance. But in their case, the last building block is changed. Instead of using a binary microfacet reflectance counted with a binomial, they propose a more physically based model with a set of real pre-calculated multi-scale Glinty NDFs. In practice, these two methods are both based on the same three fundamental building blocks, which are required by the compromises made to achieve real-time performance. First, they need a level of detail structure. The reason for that is that we can't actually just easily assign a random number to the pixel's footprint. Instead, what we need is a random numbers which are anchored to the surface of the object so that they are stable both spatially and temporally on the object's surface. So what we do is simply distribute the random numbers on the vertices of a virtual grid defined on the surface. And to allow dynamic adaptation to the size of the footprint, we also introduce a structure with discrete levels of detail. And with this, we get a set of virtual grids, all anchored on the surface, which allow us to evaluate the Glinty NDF with random numbers, while always sticking close to the scale of the pixel footprint. But to do this, it of course implies being able to interpolate between two different grids at once. And that will be the second fundamental building block we'll talk about. And finally, the last building block is the evaluation of the Glinty NDF itself from the random numbers assigned to the vertices of these grids. And this is where the two methods differ. Now in practice, if we try to use these two methods in simple cases, we quickly realize that they both have important and similar problems, all linked to these three building blocks. First, their level of detail structure can only adapt itself to the isotropic size of the pixel footprint. And for anisotropic footprints, the only solution is to manually evaluate many more samples on the grid. And that's very expensive in real rendering scenarios, where anisotropy is variable and everywhere. Secondly, we quickly observe blending artifacts visible between the levels of detail because of an incorrect choice of blending method. And lastly, we can see that the individual evaluation of their Glinty NDF is both expensive and unstable. We can observe rendering times that are highly variable when only changing the glint density. The goal of our work was to bring a solution to each of those fundamental problems, and to do so we built upon Zur and Kaplinen's framework using binomial laws. We resolved the problem of anisotropic pixel footprints at its source, thanks to a change of level of detail structure, and greatly reduced the base cost of the method. By bringing a new insight into the interpolation of binomial distributions, we solved the blending artifacts between levels of detail. And finally, by proposing a new way to approximate a draw of the binomial law in constant time, we greatly reduced the rendering time variability in all possible scenarios. So first, let's talk about anisotropy. Here we see again the level of detail structure used by Zur and Kaplinen, this time in real conditions. So for each vertex of the grids, we drew a number from a binomial distribution. The LOD method allows these glints to be both anchored on the surface while adapting to the scale of the pixel footprint, with the goal of sticking as close as possible to 1 pixel equals 1 texel on the grid. In practice, we need to evaluate and blend 2 grids per pixel, and for each grid, we need 4 binomial draws with bilinear interpolation to get a continuous signal along the surface. So in total, we need 8 binomial draws per pixel. This is still reasonable, but of course, the footprint can also be anisotropic. And in that case, the only solution is to manually integrate the footprint with many more samples, just like hardware anisotropic filtering, but without hardware acceleration. In practice, they limit their methods to a max anisotropic factor of 16, as beyond that the cost really explodes, and it's sufficient to handle most real cases, but at what cost? With GPUs being highly parallelized, all it takes is 1 pixel with a high anisotropy to slow down an entire group of threads. And this is where the biggest performance problem of these two methods lies. But we'll try something else. We're back to our isotropic LOD structure, but this time the footprint doesn't grow isotropically, it stretches in one axis. So we can go back to 1 pixel equals 1 texel in this situation too. We add a second dimension to our LOD structure, which stretches the grids to compensate for the stretching of the footprint. In doing so, we've extended from a one-dimension scaling LOD blending space to a blending space in 2 dimensions, a scaling and a stretching, and we now just need to blend between 4 grids instead of 2. But what do we do when the footprint is anisotropic, but in the different direction? We keep applying the same logic. We simply add a 3rd dimension to our LOD blending space, but this time it's a rotational axis to deal with the footprint's rotation. But we can't actually just divide this axis in discrete identical steps. If our footprint is much less anisotropic, the underlying virtual microfacets seen by the footprint barely change at all when the footprint rotates, so we need much less rotational steps. And when the footprint is much more anisotropic, the microfacets within the footprint change at a very high frequency, so we need much more steps. So instead, we use an adaptive subdivision of the rotational axis, where we double the amounts of steps for every step in the stretching axis. Thanks to this, we now have something that behaves exactly how we want. We have a new LOD structure that can adapt to anisotropic pixel footprints, always staying very close to 1 texel equals 1 pixel. But now if we naively implement this new 3-dimension LOD blending space, we would come back. Good time to drink. That was good. Oh. I should try what?
You can come up with a better fix, but not in 1 minute. So
Okay.
maybe we try it this way, okay?
Yeah, let's try. I don't think that's good enough because it's like less than half the time. Okay.
All right, so sorry for the technical difficulties. We unfortunately have to take like 5 minutes, hopefully it'll be a 5-minute break in order to fully fix this, because otherwise it will continue like this for all 4 talks, and that's not an option. So we have to take a short break, unfortunately. Sorry.
No worries.
All right, so it should be fixed by now. So let's get back into the action. So please continue, and sorry for the inconvenience, for the interruption.
Thank you. All right, so as I was saying, we now have exactly what we want, a new LOD structure that can adapt to anisotropic pixel footprints and staying very close to 1 pixel equals 1 pixel. But if we naively implement this new 3-dimension LOD blending space, we would actually have to be blending between 10 grids at once. And each grid requires 4 bilinear samples, so that's a lot. So instead, we'll do something better. If we look at the basic pattern of this blending space in the 2D stretching and rotation axis, we have a pentagon. But the most simple shape in 2 dimensions, the simplest shape, is the triangle. So let's triangulate this whole space. And now if we add back in the third dimension, each of these triangles in 3D becomes a prism with a triangular base. And each of these prisms can be divided into exactly 3 tetrahedra, which is the 3D simplex shape. So now, by simply identifying within which tetrahedron our sampling point is located and finding its barocentric coordinates within it, we can evaluate our 3D LOD blending space with only 4 grids instead of 10. So in conclusion, our new LOD structure is twice as expensive as the previous one in the isotropic case, but vastly cheaper as soon as anisotropic kicks in. And its most important feature is that it's a constant time algorithm. We always need to evaluate only 4 grids with 4 texels each, whatever the pixel footprint is. And the cherry on top is that it can also handle any possible anisotropy factor, even above 16 and up to infinity, where the other methods simply cannot go. Now let's keep going with the second fundamental building block. Now that we have our 4 different grids to evaluate, we need to determine how to properly interpolate between them. Both previous methods do this interpolation linearly between the end results of the 2 grids, and that's simply where their blending artifacts come from. Linear interpolation doesn't preserve any statistic of the interpolated distributions except for the mean, but in the case of glints, these statistics are very important. So how can we solve this? In our paper, we looked specifically into Zur and Kaplanen's framework using binomial distributions, and it so happens that in this framework, we can easily solve this issue. We introduced the concept of distributed binomial laws, which allow us to get the correct result in blue on the right, and I'll refer to the paper for more in-depth analysis, but the important thing to know is that in the end, it's a very small change to make. Instead of interpolating the outputs of the binomial draws, we interpolate the inputs and then add the results together. Intuitively, this approach simply turns the glints on or off progressively on each side. And thanks to this, we can completely eliminate the blending artifact issue within Zur and Kaplanen's framework. And finally, the last fundamental building block is the evaluation of the binomials themselves. How do we sample a binomial distribution in practice? Here we see the reference. To sample it, we need to chain together n Bernoulli trials of probability p, and this, of course, becomes impossible to do in real time when n becomes large. Instead, the common alternative is to approximate it with a Gaussian distribution. As we see here, when the parameters n and p of the binomial are large enough, the distribution becomes very close to a Gaussian. So what Zur and Kaplanen do is they compute the real binomial when n or p are small, and switch to a Gaussian when the a chosen criteria is crossed. But this creates a hard visible seam in between the 2 regions, and it still implies manually looping a certain amount of Bernoulli trials before transitioning. And more importantly, it still means a variable amount of iterations. And as I've said before, on GPUs that's very bad. Here we've measured the variance in timings observed for a fixed scene when only changing the microfacet density parameter. We introduce a new binomial approximation to solve this issue. It evaluates in constant time on both sides with a continuous transition between the 2, allowing us to drastically reduce the instability of the performance. Our approximation is pretty simple. We start with doing a single Bernoulli trial using the probability of having at least 1 success in the binomial. Separately, we also do a Gaussian approximation of the binomial law, but knowing that we already have 1 success, so we decrease n by 1 and add 1 to the result. And now if we multiply both, we get the gated Gaussian approximation of the binomial law in constant time. It correctly reproduces the stochastic behavior of the binomial law in the small numbers and converges to the same Gaussian distribution as the binomial law when n grows to infinity. And that's it. We've now seen how to bring key improvements to the 3 fundamental building blocks of these real-time glint rendering methods. Thanks to our anisotropic level of detail structure and thanks to our new binomial approximation, we get a very significant performance improvement in real scenes compared to previous methods. Here we've measured these timings on an RTX 2080 at 1080p, sorry. Additionally, this performance is now almost completely stable. Our paper also brings other improvements that I don't have the time to get into today. For example, thanks to our performance improvements, we can afford to have glints that appear and disappear smoothly, which Zur and Kaplanen couldn't do. Thanks to this, we can compare our method to that of Sherman and others which we consider as the state-of-the-art result for real-time glints when it comes to quality, because of their physically based pre-calculated NDFs. And it turns out that even in our less physically based setup, with binomial glints, we can obtain results that are identical to theirs. And our other big improvement in the paper is a very simple NDF formulation which allows us to target any continuous NDF, including GGX, whereas both previous methods are limited to the Beckman NDF. This is what allowed us to integrate our method in Unity's high-definition render pipeline, where we put together finally, we give, thank you. Finally, we give our complete source code for re-implementation, as well as the demo you just saw, and another benchmark demo where you can compare the three methods together. That's it. Thank you very much for your attention, and I'll be happy to answer a very little amount of questions.
Right, thank you for the great talk. We're a little bit pressed on time, unfortunately, but I definitely want to take at least one question. Very little questions. Is there any question from the audience? Okay, then
that's good. I'm scared of questions.
But then I'll ask one. Sorry.
Oh, okay.
What about post-processing? Right? I don't think you're using post-processing at the moment in the pipeline, because if there's any sort of image filter like TAA or upscaling or even denoising or something, would the glints survive?
So we are using one post-process here, which is a bloom, because we want to show when the intensity is higher than 1 for HDR. And actually, in this video, we're actually using all the post-processing features of HDRP. So with TAA, I've seen that you need to tweak a bit the parameters to not make it completely smooth out the glints, because it changes very fast. But it's feasible. It's only when you put the parameters like very in weird positions, then you could get something weird, yeah.
All right, thank you. Right, then let's thank the speaker again. And we're moving on to the second paper in session. So now we're going to learn why we all used to sample the GX distribution wrong and how you can do better. So the paper is called Sampling Visible GGX Normals with Spherical Caps. And it will be presented by Jonathan Dupuy. And he's also from Intel, because apparently it's a sponsored session from Intel with 3 papers from them. So if you're ready to go.
Can you hear me? Yes.
Perfect, then take it away.
Okay, thank you for the introduction. Okay, so yeah, this is a presentation for a sampling paper I co-wrote with Anis, who's also here at the conference. It's actually the shortest paper I've ever written for a full track paper. The whole content of the paper is on this slide. It's only 6 pages long. So the reason why it's so short is because the contribution is very specialized for path tracing. So speaking of which, if you have a path tracer, you have your rays that you use to intersect surfaces, most probably triangles. And then you have materials that will give the appearance of the surface. And the way this works is that whenever your ray hits the surface, it will deviate in a certain direction that is predicted by the material. And so if you're interested in having a state-of-the-art material model, you probably have support for GGX BRDFs. And if you do, then you probably have somewhere in your code base this little snippet that is due to Eric Heitz. And our contribution is to actually propose a different implementation that is both simpler, so I guess you can already see it's shorter, and also faster. So at this point I want to emphasize that this is not the result of optimization over the original code, but it's rather due to a novel insight that leads to a completely different implementation. And this insight is related to linking the GGX VNDF, which is the code that is due to Eric, with spherical caps. And so this is what I want to focus on in the remainder of this presentation. So I'm going to start by talking about the GGX VNDF, two acronyms. So if you're not familiar with this, it can be a bit scary. So GGX first, so that's a distribution that's involved in microfacet theory. So microfacet theory, it was introduced by Bruce Walton and colleagues in 2007. So microfacet theory is a physical framework to explain the appearance of surfaces by basically explaining that the appearance is the result of interactions between a microsurface and your incident rays. And GGX is a distribution to describe the distribution of orientations of the facets that compose the surface. And another way to see it is that this distribution encodes the distribution of normals that lie at the surface of an ellipsoid. And there are some very nice insights you can get from this theory, like for instance, if you stretch the surface, you'll get a rougher appearance, and conversely, if you flatten it, you'll get a shinier appearance. What you can also do is stretch it anisotropically to create some brush metal effects, such as this and this. So in the original paper, Bruce Walter introduced an important sampling mechanism as well, which consists of sampling a random normal, so a green vector here, at the surface of the ellipsoid. And the problem is this important sampling mechanism introduces some artifacts such as fireflies that you can see here, hopefully. And this was fixed by the paper of Eric that I talked about in the introduction, by introducing this VNDF sampler. And basically the idea is, rather than randomly picking a green vector at the surface of the ellipsoid, you're going to pick a green vector that lies at the intersection of the projection of the ellipsoid in your incident direction and the ellipsoid. So that would be the green area. And what you have to do basically is to uniformly sample this projected area. And the way he does so is by in 3 steps. So first you have the ellipsoid. He uses an invariant to re-express the problem into that of sampling a hemisphere. So you basically recompress the ellipsoid to an hemisphere. This also warps the incident direction. I hope you can see that the red line isn't quite the same. And then he has an algorithm to sample solely the hemisphere, which has less degrees of freedom. And then he applies the inverse transformation to warp back to the ellipsoid. So basically, in terms of code, it's essentially 3 lines. So first, you warp the incident direction to re-express the problem into that of sampling a hemisphere, sample the hemisphere, and then warp back to the ellipsoid. And so what we contribute to in this work is to the replacement of this specific routine, sampling the hemisphere. So this is the original code of Eric. Here's a quick animation to show how it works. Left click, okay. So here I'm using an orthographic projection and looking at the hemisphere. Here I'm going to freeze the viewpoint so you can see the projected area. And then the code allows you to map 2 random numbers into this green area, sample it, and then re-express it back to at the surface of the hemisphere. And this works for arbitrary incident directions. So here I'm changing the incident direction. Yep, and that's it. Okay, so that's for the GGX VNDF. So now on to the insights and the relation to spherical caps. I'm going to explain what spherical caps are in just a minute. So what we did was to consider the original sampling scheme of Eric, and we looked at just one sample and assumed that the hemisphere would act as a perfect mirror. So this means that we can compute from the surface normal in green and the red direction an orange direction, which corresponds to the mirror reflection of the incident direction. And we plot this direction as a point at the surface of the sphere. So if you do this for various samples, you get more and more points. So I'm doing it more and more. And what you can notice is that as we add in more samples, it seems that the samples are starting to cover the entire sphere. almost actually. There's an area here under this particular plane in gray that isn't covered. It doesn't have any samples. And this particular orange geometry here, it's called a spherical cap. So it's just a sphere that is restricted to by a plane, and you're only looking at the area that's above this plane. And so it turns out that in the paper we show two things. So a hemispherical mirror reflects parallel rays uniformly and within a spherical cap. So I have an entire proof in the paper by using Jacobians. But so intuitively, for the uniform part, it's known that if you look into a spherical mirror, you know that the incident rays will be reflected uniformly. And since a hemisphere is a restriction of the sphere, then it's obviously uniform too. And for the spherical cap section, I can show you a few examples. So what we show is that the plane of that cuts off the sphere is completely determined by the elevation of the incident direction. So if we change the incident direction, the plane, if we go downwards, the plane is going to go up to this limit case where you're looking at the hemisphere above, and you only have some directions that go straight up. So that's a Dirac distribution here. And conversely, if you go upwards, up to the upward direction, you cover the entire sphere, and here you're sampling the sphere uniformly. So just a bit of intuitions, because I know this can be counterintuitive. There's an IKEA shop next to the university, and they sell this lamp. And so if you look at this lamp from a particular direction, so here I'm looking from above, so you're going to see all the direction above it. So if you have this environment here around you, this is what you're going to see in the lamp. And if I move around the lamp, so if I look horizontally, you'll get this restriction, and this is what's going to happen, is you're going to see half of the environment. And again, if you go downwards, you're going to restrict it a bit more. So here's an animation to show everything for various observation conditions. So here I'm going upwards. I'm just showing the projected area again, sampling it. So here in orange, you have the reflected directions that sample the entire sphere. And this is why, when I go back, here you see the entire environment. So you have the ceiling at the center, the doors in the middle, and at the boundaries you have the floor. So now I'm going rotating around the hemisphere. So here we can see half of it. And then going downwards again, you get restriction that gets more and more important. Okay, so what do we do with this? We build our sampling algorithm based on this particular insight. So the idea is, since you have these red directions and these green directions, from these two quantities you can infer the orange directions on the spherical cap. What you can also do is, if you have the orange directions and the red ones, you can compute the green directions, which are the normals that we want to sample. And the way this works is as follows. So you start by sampling, randomly sampling the spherical cap. And then, so I'm plotting it here on the hemisphere, so you get a random direction here. You add, and then you compute the half vector. So you just add the incident direction, and then the sum of the two directions is directly proportional to the normal. And so if you normalize this direction, you get a normal at the surface of the hemisphere that is directly sampling the GGX VNDF. So that's it. You just have to return this half vector. And so if you look at our code, this is exactly what we do. So we sample a spherical cap. These lines of code just place an orange sample at the surface of the cap, and then we just add the two directions without normalizing it. I just discuss it's a quick optimization that I discussed in the paper, and that's all we have to do. And so it's simpler than the method of Eric, because Eric has three steps. So first he needs to build an orthonormal basis around this green area, which has a singularity if you're looking above the hemisphere. Then you have to sample this area that has, well, at least a more complicated shape than that of a spherical cap, so there's more arithmetic involved in there. And then you have to reproject at the surface of the hemisphere. So there's 3 steps compared to us, which is only 2. And so in terms of speed, so we benched our code. So first in a standalone fashion, where we ran both codes 100 times, and we took the median time on both a CPU, and then there we measured a 36% improvement, and also on a GPU, an Intel Arc, and that resulted in 40% faster. If you were to use another GPU, you would also observe similar speedups. Okay, and then we did some renderings in PBRT4. so we have the same variance reduction, so no additional noise compared to the original method. And then we also did some benchmarks, performance benchmarks, and here we observed some much less important speedups. And the reason was that basically when you're doing path tracing with global illumination, the bottleneck isn't the material sampler, it's the ray triangle intersection. So, I mean, the takeaway is that best case scenario, you'll get a 40% improvement if you're bottlenecked by your material sampler, and if not, you'll get a much less significant improvement, but it will be systematic. So there's no good reason not to use it, I would say, subjectively. Okay, that's it for me. Thank you very much.
Well, thank you for the great talk as well. Are there any questions from the audience? Yes. You get the Cube of Destiny.
Thanks. Thank you for the nice presentation. I'm wondering if you even need to compute the half vector in the end, because oftentimes when you do this VNDF sampling, right after that you compute the reflection vector again, because that's where you will trace your ray.
Yeah, so that's a good question. So there's a bit of a subtlety, and I had this question before. So when you're sampling the hemisphere, you're basically sampling the VNDF of a GGX with roughness 1. Okay, and for other configurations, you need to stretch the ellipsoid, and so this stretching operation composed with the specular reflection is not equivalent to stretching the outgoing directions directly from the hemisphere.
Okay, that makes sense. Thanks.
Are there any more questions? Just you?
Sorry.
So on that point, because I had the question about how you handle different roughnesses, is there also a step afterwards to then warp it to an ellipsoid?
Yeah, so actually, yeah, maybe that wasn't super clear. Let's go back to the general algorithm. Okay, so that's basically, that's your sampler. Yes. That's the sampler you're going to call. And in this sampler, there's the hemisphere sampling routine. So you're not supposed to call this code directly, you're supposed to call this one. And actually, the reason why, well, since you asked, the reason why I'm not normalizing the half vector is because there's a normalize right here at line 8, so you don't need to do it twice.
Yeah, makes sense.
Yeah.
Thank you so much.
Are there any more questions? Doesn't seem so. So I have one more question.
Yep.
Do you think you can extend the same idea to transmission?
Yes. Yeah.
Okay.
So it's completely transparent. So what you do is here you sample a normal, and you can use this normal to either reflect, refract, or you can also use some other fancier BRDFs to control the final bounce. So it's you can use it in conductors, and actually at the end I have sorry, I went too far here. So here you have some conductors, and here's some dielectrics. Cool. So it's completely transparent.
Thanks. So let's thank the speaker again for the great talk. I will get the cube in a second. All right, so we're on to our third paper in session. And you probably all by now heard about something called nanites, and we all know it did a great thing for the HPG YouTube channel, which was the biggest impact of it, of course. So now we're looking into how we can actually make a similar idea work in ray tracing. So the paper is called Real-Time Ray Tracing of Micropoly Geometry with Hierarchical Level of Detail, and it's going to be presented by Carsten Benthin. So please take it away.
Thanks for the introduction. Can you hear me? Okay, one sec. Okay, so hey, I'm Carsten, and today I would like to present our work on real-time ray tracing of micropoly geometry with hierarchical level of detail. And this is joint work with Christoph Peters, who actually sits over there and had the original idea. So if you after the talk think this method is crap, right, just don't blame me, blame him. Okay, let me start by highlighting the state of the art in terms of handling extreme geometric complexity in real time. And that's nanite. I mean, nanite is simply awesome. And as nanite's approach of hierarchical LOD has been the fundamental inspiration of our work, I would like to provide a quick recap on how nanite actually works. So in general, nanite first partitions the input geometry into small triangle clusters and applies logic compression to reduce their memory footprint. In our little example here, the input mesh of 16 triangles is subdivided into 4 clusters with 4 triangles each. In the next step, Nanite builds a cluster-based hierarchical LOD structure by following a merge and split strategy. In our example here, the 4 clusters get merged into a new cluster, and the geometry gets simplified while preserving the boundary edges. Finally, the simplified cluster gets split into 2 smaller clusters. So in general, we have 4 input clusters that will produce 2 output clusters. And this exactly turns the hierarchy into a DAG, a directed acyclic graph, where a child node, for example, can have multiple parents. So in terms of rendering, Nanite traverses the DAG and essentially performs a cut through it, indicated here by the red line in our example. This cut selects a subset of clusters that fulfill certain view-dependent LOD requirements. And in the next step, the number of clusters in the subset are further reduced by frustum and occlusion culling. And finally, the remaining clusters are decompressed and the resulting triangles are processed by a rasterizer. So on average, Nanite roughly rasterizes 20 million triangles per frame. Now, the issue is that Nanite works great with a rasterization-based backend in mind. But it's not really straightforward how to combine the per-frame cluster-based hierarchical LOD selection with hardware-accelerated ray tracing. The problem is that the decompressed cluster geometry needs to be turned very quickly into some form of bottom-level acceleration structure, short BLAS, that the ray tracing hardware can actually consume. So what are our options here? Option 1, forget per-frame LOD. Put a fixed geometry resolution, most likely the highest, into 1 or more BLASs, and reuse those for rendering all frames. Well, the problem is that the BLAS memory footprint is significantly less dense than the lossy compressed cluster representation. So one runs out of GPU memory pretty quickly. Also, modifying the scene, for example, for streaming cluster data will be pretty difficult. And obviously, with a fixed resolution, one ends up with geometric aliasing. And by the way, some form of this option is what Nanite does today. Option 2. So we do actually per-frame LOD. We traverse the DAG, select and decompress clusters, and put the resulting triangles into 1 or more BLASs, and trigger a BLAS rebuild, which in almost all cases internally means a BVH rebuild. Problem is that from frame to frame, different clusters will be selected. So the resulting mesh topology will change, and that will require a full BVH rebuild instead of a BVH refit operation. And unfortunately, today's BVH rebuild performance, even with reduced quality, is not fast enough. And just to give you an example here, let's say you have 20 million triangles and you have a BVH rebuild performance of 400 million triangles. That would still take 50 milliseconds, so that is way too slow for real time. And this is what our approach exactly tackles here. And so let me give you a brief overview of our approach. So similar to Nanite, it consists of 2 phases, right? A CPU-based preprocessing phase and a per-frame phase, which is exclusively executed on the GPU. In the following, I would like to present a little more detail, so I'm starting with the preprocessing phase. So the preprocessing phase consists of 3 steps: the initial cluster generation, creating the hierarchy over these clusters, and lossy compression of the cluster data. And all of these steps are quite similar to Nanite, but our implementation is a little bit more tailored towards ray tracing. So before we actually generate the clusters, the first step that we do is to convert all triangles of all input meshes into triangle pairs, which we call simply quads from now on. And there are 2 reasons for doing that. First, for complex micropoly geometry, the probability that the neighboring triangles share a common edge and can be turned into a quad is extremely high, so it makes perfect sense to use quad at this point to reduce the memory footprint. Second, well, the ray tracing hardware units of our target GPU architecture actually support triangle pairs at the leaf level, so this is another argument for using quads at this point here. So once we have our list of quads, we build a simple BVH over these. And then we traverse the BVH top-down to extract subtrees that have 128 or less quads at the leaf level. And we will turn exactly these subtrees into clusters. So the reason for using a BVH to extract clusters is that it makes sure that clusters consist of spatial coherent quads, as shown in this example here on the right. This minimizes the bounding box overlap between adjacent clusters, which is beneficial when we later build a BVH over these. Okay, so we have now our list of clusters. The next step is to create a hierarchy over these. And similar to Nanite, the hierarchy is created by merging clusters. And for identifying pairs of clusters which should be merged, we use a modified iterative bottom-up BVH builder based on the block algorithm. So for a given cluster, the block algorithm, you don't need to know what it exactly does, but it allows us to quickly identify from all adjacent clusters around the current one, the one where the area of the bounding box after a potential merge would be the smallest. So essentially, we are again trying to reduce the overlap between neighboring clusters, which is always beneficial for BVH quality. So once selected, the cluster pair is merged into a new cluster, and the underlying geometry is simplified while preserving the boundary edges. So this entire bottom-up merging process would create a binary tree, but unfortunately, cluster merges can fail. And the reason for that is that the number of quads after simplification can exceed our limit of 128 quads per cluster. And the reason for the insufficient simplification is due to the high number of boundary edges. And in this case, we follow Nanite's approach of splitting the merge cluster again to reduce the number of boundary edges, as shown here in this example. So on the left here, we have two clusters with the shared boundary vertices are marked red. The middle one is the merge cluster, and the right is the simplified merge cluster split in a different manner, and thereby reducing the number of boundary vertices. So essentially, the cluster splitting reduces the probability of failed simplifications higher up in the hierarchy, but at the same time turns the hierarchy from a binary tree representation into a binary DAG representation. But even with cluster splitting, at some point simplification of clusters will no longer be possible, in particular way up in the hierarchy. So the remaining unmergeable kind of clusters will become the root nodes of our binary DAG. And this is in contrast to a binary tree where you only have one root, right? Here we have multiple roots for the binary DAG, but they are also easy to handle. Okay, so the final step of our pre-processing phase is the lossy compression of our clusters. But what data does our cluster actually contain? So our representation is super simple. It's nothing more than a quad mesh plus some metadata. And we therefore apply a very simple lossy compressing scheme. We quantize all vertices with respect to the object's bounding box and using 16 bits per dimension. And for the vertex indices, we use 8 bits. So in other words, a vertex takes 6 bytes, and the 4 indices of a quad take 4 bytes. So on average, a triangle requires 46 bytes, or in other words, we can put roughly 160 to 220 million triangles into a gigabyte of memory. And as we preserve the boundary edges per cluster and quantize all vertices of an object, and therefore all contained clusters in this object the same way, we preserve water tightness within this particular object. But we cannot preserve water tightness across objects because they use different bounding boxes. Okay, so this concludes the pre-processing phase. Now switch over to the per frame phase, which is again exclusively executed on the GPU. It consists of 3 steps, right? The LOD cluster selection, the cluster decompression in the local cluster BVH build, and the fusing of the cluster BVHs. Okay, in terms of LOD selection, it's pretty straightforward. We do a parallel traverse, top-down traverse of our binary DAG, starting from the root nodes, and at each traversal step, we take the bounding box of the cluster and project it to the image plane, right? And then we take the 2D bounding box of the projection, compute its diagonal, and if this diagonal is less than a predefined threshold, in our paper we use 24 pixels, right? We add this particular cluster to the list of clusters which need to be decompressed in the next step. And one important point I would like to make here is that clusters outside the frustum, right, they cannot be culled because we need them for secondary arrays, right? If the arrays bounce around, they could potentially touch all clusters. And this is quite in contrast to an rasterization-based Nanite approach, which aggressively culls these clusters. So what we instead do, we just assign a coarser LOD level to all clusters outside the view frustum. Okay, and before we look into more detail at the cluster decompression in the per cluster BVH build, a few words on our GPU target architecture, because this will be important for this step. So our target is an Intel Arc GPU, and the underlying ray tracing hardware unit uses a 6-wide quantized BVH, which we call simply QBH6 here, as an acceleration structure. So an inner QBH6 node requires 64 bytes, and a leaf node, because it stores uncompressed triangle pair / quad data, requires 64 bytes as well. And if you wonder why it's a 6-wide BVH and not a 4-wide or 8-wide, 6-wide was, let's say, the maximum wideness that we could squeeze into 64 bytes. And one important point here is that the QBH6 representation, because it stores uncompressed data, is roughly 5x larger than the lossy compressed cluster representation. So we have a memory expansion when we go from the cluster representation to the QBH6 representation. Okay, so the output of the previous LOD cluster selection step was a list of clusters that contain the right geometry representation for the given frame. Now what we need to do is to decompress each of these clusters and convert them to a QBH6 representation. So here are the exact steps. We load the lossy compressed cluster data, decompress it, but store the resulting quads into shared local memory. Then we trigger a local BVH build process over these quads and store the resulting QBH6 out to global memory. The important point here is we omitting the bandwidth intensive step of writing out the decompressed quad data first to global memory before building the QBH6. So we try to stay as much as possible into shared local memory because this is way faster. So in our little example here, the 6 clusters on the right, 6 clusters with 6 quads on the right here will be directly converted to the exact QBH6 layout as shown here on the right side. And one interesting fact is that we can really optimize this step pretty intensively. So in terms of performance, we can load the compressed data, decompress it, and write out the QBH6 almost at 75 to 80% of a memory copy speed. So basically, this is blazing fast. Okay, so this is the final phase of the frame GPU phase. So we have all the the cluster QBH6 lying around in global memory, and we just need to kind of connect them together, kind of fuse them together into a single QBH6. And we also went for the most simple approach. We simply built a kind of a top-level QBH6 over the cluster QBH6s to connect them. And keep in mind that the number of clusters will be significantly less than the number of quads in the scene. So using a full BVH rebuild is really a viable option at this point here. Also, a full BVH build makes adding and removing clusters per frame very easy. So, for example, makes streaming kind of trivial. Okay, let's have a quick look at results here. As mentioned before, I use an Intel Arc here with 16 GB of memory as GPU target. In terms of software, we integrated everything into a modified version of Embry 4.0. And the main reason for doing that is that Embry is open source and we can modify as we want, right? So, and therefore we can kind of bypass the current DXR and Vulkan API restrictions. So what we simply did is we added another primitive type to Embry, and this is our lossy compressed clusters. Okay, so this here is a little example. It's a 200 million triangle example scene running at full HD resolution with 4 samples per pixel at around 60 frames per second. The right side shows the tessellation. When we got closer, the tessellation changes from a lower to higher resolution. And now the right side actually shows the actual clusters, and the change in color means we use a different cluster for this particular part of the geometry. And here is an LOD visualization, and the brighter the red, the finer the LOD level. Again, when zooming into the darker parts, they become brighter as a finer LOD level and a higher geometry resolution is used. And we obviously not limit to primary visibility. This is pathing plus denoising, right? With 1 sample per pixel, denoising adds roughly 10 millisecond overhead, and it runs at 20 frames. And this is just a larger scene with roughly 500 million triangles. And also we stay at around, hard to read, 20-something frames per second. Okay, let's have a more detailed look at the actual per frame cost. Again, the per frame GPU phase consists of the LOD selection, the cluster decompression, the local cluster BVH build, and the third step is the fusing of the clusters. And if you look at these numbers, they are all very fast, with the second being the most costly one. And if you add them up, right, you get roughly a per frame overhead of 5.7 to 9 milliseconds, which is kind of okayish for real-time applications. So one important point here is that the second and third step actually build a full BVH over the triangle/quartz contained in the selected clusters per frame. Now, if one adds the cost of these two together and computes the BVH build performance and compares it to building a BVH over the individual quartz without leveraging the cluster hierarchy, one gets an order of magnitude improvement, right? And this is quite significant and is the essential reason why our per frame LOD selection approach actually works really well. And we can make use of this, right? We can actually support fully dynamic content. Here we have 50K B-spline and Gregory patches that for each frame get on-the-fly tessellated based on the current LOD settings. And the tessellation results are directly converted in our lossy compressed cluster format and stored out to global memory. And that, from that point on, it's the same procedure as before. The clusters get decompressed, the cluster BVHs get built and finally fused together. And the BVH build process does not know anything about that the clusters has been on-the-fly generated. And here everything runs at roughly 60 frames per second at full HD resolution with 4 samples per pixel. Okay, so let me quickly conclude. Cluster-based class construction / BVH construction is extremely fast. Why it is so fast? And the reason for that, it's another incarnation of a build from hierarchy, right? And Laurent had a famous paper almost a decade ago and built from hierarchy. And it's basically the essential ingredient why you get a 10x speed up here, right? You have to kind of restrict the BVH build first to a local partitioning of the C in the clusters, right? And then you fuse the cluster BVHs together. And if you do that, you're way, way, way faster than doing a standard BVH build of all the individual triangles or quads. Okay, and with that, we're getting really close to real-time hierarchical level of detail with hardware-accelerated ray tracing, right? We have an overhead of 5 to 9 milliseconds, which is honestly a little bit too much for games, right? But obviously the code could get optimized and faster hardware, yada yada, right? So we're getting close there, right? There is basic light at the end of the tunnel. And one important thing I would like to mention is that in terms of complex micropoly geometry, we should not deal with individual triangles or quads, right? We should use a coarser granularity. And I think something like a lossy compressed cluster mesh should be a new primitive that everyone should use. Okay, quickly in terms of future work, I mean, it's pretty obvious. Our lossy compression scheme is probably not that advanced, right? So something better, we should use something better, something like delta encoding with prediction or something like hierarchical encoding, right? And the same goes also for the hardware-supported geometry representation in the BLAS, right? But one important point I would like to make here is that these two don't have to be the same, right? As we've shown today, we can convert from one to the other on the fly per frame. And as I mentioned before, we should kind of standardize the lossy compressed cluster mesh primitive type to make it vendor agnostic. So this means adding some special DXR Vulkan API extension. Okay, and with that, I'm happy to take your questions.
Thanks for the great talk. Are there any questions from the audience? Right. Oh, I need to throw. Give me a sec.
I'll just project. Really nice.
For the online people, we need. Okay, I'll not throw.
Oh, okay.
Oh, you have a microphone anyway.
I did have a microphone. Yes, true. Yeah, really nice talk.
Thank you.
Would there be any benefit at all using refitting at any point? Is there any way that could help?
Refitting is a little bit tricky due to the binary DAG nature. I mean, if you would have a binary tree, this would be way easier. With the binary DAG, it gets a little bit more tricky. It's doable, but it's probably more kind of future work.
Okay.
But the BVH rebuild performance, let's say, if you do it over the clusters, is so fast. I can go back there, roughly 1 or 2 milliseconds. And this is kind of almost unoptimized code. So,
okay. So
it's not really the bottleneck.
Okay, thank you.
For the dynamic geometry,
Yeah.
To keep things performant, did you need to have same topology? Like if the topology changes, does the clustering change in a way that lowers performance? Or?
So the base geometry of the dynamic example that I've shown here are basically B-spline patches and Gregory patches. And they just get evaluated based on certain LOD, distance from the viewer, right, projecting the bounding box on the image plane, right? Then you select the tessellation level or the evaluation level, and based on that you get your tessellation, right? And then you convert this to the lossy compressed cluster format. And your question was whether this impacts performance?
I guess in a more typical scenario where you start with high resolution triangles and you want to do this kind of clustering.
Okay.
If you change topology, would that have any effect on the performance of the clustering?
Of the initial. So in general, as always for ray tracing, it's you should avoid long diagonal, let's say, triangles. So if you change the topology in such a way that you get these kind of artificial kind of triangles, that is bad for BVH quality, right? So, but in general, if you deal with micropoly geometry where your tessellation is roughly the same, I don't think that changing, let's say, the connection between the vertices does anything to the BVH quality. I don't think so. If this answers your question, or we can take it up maybe in after
I can
the
ask you after.
Okay.
Are there any more questions? Right, so assuming you would get hardware support for the quantized BVH, do you think there's still room for rasterization?
Room for rasterization? Yeah, rasterization won't go anywhere anytime soon, to be honest. I mean, there is 20, 30, 40 years of legacy, right? No way, right? But there's, I guess, it's a little bit, my personal opinion, there's a slow shift towards ray tracing going over the years, right? It's not as fast as for the, let's say, the movie and special effects industry where it happened within 10 years. For the game stuff, it will probably take a little bit longer. But it's just my personal take on it.
And regarding the differences of nanite, is it just works so much better for rasterization? Is it not a good fit for ray tracing? What do you think? Because all of the overhead for the BVH building?
Yeah,
or is there some other secret sauce going on in nanite?
That's a good point. So I don't think that the initial clustering has been really optimized in nanite for ray tracing, right? Because it's kind of how you group your triangles or quads together. If they take a lot of space, right, this would be bad for ray tracing because the bounding boxes would overlap between neighboring clusters, right? So I don't think that the nanite guys paid that much attention because it doesn't really matter from a rasterization-based approach. Right, this would be my take. But Christoph,
so yeah, I can add a bit to that. The nanite mesh preprocessing is very focused on the topology of the geometry. So as you said, it doesn't really care about bounding boxes. So that's basically the key motivation why we did it differently. But with that said, I'm honestly not sure if it might actually get better if you would do exactly what nanite does. I mean, we did not want to somehow integrate this into Unreal Engine because it's just a huge code base to work with. So we did something from scratch, and doing it based on block was the more straightforward option. But yeah, nanite preprocessing may still work better with this, in spite of not caring about bounding boxes.
Thank you. So if there's no further questions, then let's thank the authors again. It's a great paper. So then we will be moving on to our last paper in session. The paper is called Compressed Opacity Maps for Ray Tracing, or in other words, how to get rid of that nasty any-hit shader. And it will be presented by Simon Fenney. And we haven't tested the setup before, so there might be more technical stuff coming.
Do apologize. Do I want you to do extend? Extend? Oh, right.
Just start the presentation.
Oh, right. Okay. So,
all right.
Right.
Go ahead. Sorry.
Good morning. So today we'll be presenting our paper, Compressed Opacity Maps for Ray Tracing. So we aim to cover the following points. Well, the problem we're addressing, what are opacity maps and how do they help, and why would we want to compress them and how. So what is the issue? Well, in 2020, Gruen et al. Described the problem, but that was in lockdown, so I'm sure we could all do with a reminder. And the answer is basically alpha tests, particularly if you've got a lot of alpha tests. So standard triangles are useful for your typical teapot, bunny, dragon model, but artists want to do things like flora, complicated shapes on leaves, etc., building components, grills, windows, and maybe damage effects. But modeling these with solid triangles would be costly. So the solution, like rasterization, is to use alpha testing. Now, the standard APIs like DXR and Vulkan RT support alpha testing via the AnyHit shader. Personally, I think confirm hit would need a better name. But so when when a ray hits a triangle that needs to be alpha tested, it basically then launches the AnyHit shader, which makes a decision whether you want to actually keep the hit, in which case you proceed as if it was a solid triangle, or you reject it and go back to the traversal. So this is really quite flexible. You can do it via looking up textures, or you could do some computation, say put a circle on your triangle. But it is an expensive overhead. Interrupting your acceleration structure traversal incurs a penalty because memory is slow. You may need to hide many hundreds of clock cycles of latency. And that could be due to, well, just scheduling that AnyHit shader, having potential texture cache misses, or even just restarting the Anyway, then also there may be many, many layers of alpha testing. For example, in San Miguel or the physically based rendering landscape scene, if we just zoom in on this section, this is just showing the average number of alpha tests just for the primary rays. And you can see regions which have opaque triangles, black, which basically none at all. But you can also get regions where you are doing, well, upwards of 6 to 10 tests. So it's a significant overhead. So how do we solve this? Well, we do some pre-computation, basically, and generate opacity masks. So in 2020, Gruen et al. Presented opacity masks, which is basically you take any alpha-tested triangle and can pre-compute an n-squared triangle grid of subtriangles. And each subtriangle is marked with one of three states: T for completely transparent, O for completely opaque, or C for check using an AnyHit shader. Now the T and O states completely avoid running the AnyHit shader. The mask can be stored with the triangle acceleration structure, and then the ray triangle tester is modified to read that mask. So in this particular example, you get about a 53% saving in alpha test launches, AnyHit shader launches. So the question is, can we do better? So Gruen et al., they looked at 4 alpha textures and showed that higher resolutions get you greater savings. We confirmed that with a set of 170 textures, and you can basically see that the gains diminish. So we've got cases where we've got a 32 by 32, and if you jump to a 64 by 64, you get about a 6% saving. But if you quadruple the storage again, the saving only increases by 3 or 4%. But it certainly helps in alpha-tested scenes. Going back to the landscape scene, putting on an opacity map, well, simulation here, you can see that the number of tests has plummeted to typically less than 1 per ray. So, can we do better? So, why do individual triangles? And can we do better than 2 bits per region? So we started looking at individual triangles, but flora models commonly use meshes of at least 2 triangles, and sometimes quite weirdly. So can we exploit the coherence? Some hardware systems, another observation, some hardware systems, Intel's imaginations, store or test pairs of adjacent triangles with a shared edge. Now there's several reasons for wanting to do that. There's some details down on the poster in the foyer. But basically, the AABB of a pair of triangles is rarely much bigger than either of the 2 constituents. Testing an array against a pair of triangles can share the maths of the shared edge, and you get a 33% reduction in vertex storage. I mean, you can do more if you do strips, but trying to find those drops off very rapidly. So another observation. So Gruen et al., they stored it as 2 bits per state. They did note it could be compressed into less data. Now we read that as meaning log 3 bits per subtriangle. So you want random access, so maybe you would store 5 subtriangles for every byte, which allows completely random content. But textures are rarely noise, so a smaller footprint seemed feasible. You want a higher resolution, so that gives you larger savings, but that comes at a storage cost. So compression is desirable, but you need fast random access, so that rules out a number of compression schemes. We also felt that you want to store the opacity map together with the vertex XYZ data for efficiency. You don't want the additional latency of going out and fetching that data after you've made your decision that you'll possibly hit the triangle. And it probably should be about the same size as the vertex data because you don't want the additional storage and bandwidth. So our approach was to, well, we considered taking pairs of triangles, but rather than storing them as 2 individual maps, storing them as a combined square map using square subregions. And also was to bring back vector quantization that was used in computer graphics some time ago. So just looking at some examples of some square opacity maps being mapped to 2 triangles, we expect there to be similar behavior across the shared edge. And we also think they should be frequency limited. There'd be no instant transitions from completely transparent to completely opaque. We refer to this in the paper as the continuity assumption. Now, we want to compress and decompress them, but the decompression, like texture compression, needs to be fast and provide random access. We want to avoid any additional sort of clock cycles in decoding. And we also would like the decompression to be cheap, small, and because it's likely to be in hardware and PPA rules, especially in the system on chip area. But the compression can be lossy. Provided it's conservative, you can safely replace an opaque with a check, but you can't go the other way around. But you don't want too many lossy substitutions because that simply undoes the benefits of the opacity map in the first place. So going back to VQ, so it was used in texture compression in the late 1990s. Beers et al. Sort of introduced it in 1996. Sega Dreamcast used it for 2-bit per pixel and 1-bit per pixel texture compression. And you can go back earlier if you count palletized textures. It is a lossy compression scheme. Basically, the pigeonhole principle says it must be. But it is a very, very simple decoding algorithm. For example, if we have 2x2 vectors, you store a half-resolution index map containing locations inside a vector codebook, and that returns a, say, for example, 2x2 vector of colors. So why did VQ disappear? Well, it kind of fell out of fashion. The cost of hiding that second vector codebook lookup was just too costly. For example, Dreamcast had a second texture cache entirely dedicated for the codebook. Also, the compressor is a global process, but that's not so much of an issue here. So other schemes like S3TC, PVRTC took over because there was no second dependent memory lookup. But if the index map and the codebook are loaded together, the latency is eliminated entirely, so that's a win. So we started an initial investigation using 2x2 vectors. Our target was 1 bit per region using a fixed storage of 256 bits, which is typically about half a cache line or on a GPU or slightly less than the XYZ data for a pair of triangles, which then forces a 16x16 resolution. So we made some more observations of the test data. So uniform 2x2 vectors are really common. They typically occur with about a 11 to 30% frequency. And we also often found symmetry across the test data. So this is a leaf from San Miguel, and you can see that the vectors circled in red reappear in the quadrants, but each time rotated by an extra 90 degrees. And other data, we found that there was reflections around X and Y or around diagonals. So we can use this to reduce the size of the stored codebook. Which brings us on to how do we represent each vector in the codebook. Now, it may appear that there are 81 different possibilities for a 2x2, so do we really need 7 bits to represent it? But by the continuity assumption, you can't have both O and T states in the same 2x2 vector. So it turns out there are only 31 possibilities, so we can use a virtually ideal 5 bits, which leads to an utterly trivial encoding where you have 1 bit to determine which pair of choices you've got, and then 4 1-bit indices. So we also need to store the transformations for 3 of the quadrants. So these are chosen from a palette of 8, and each of these choices can be generated by combining 3 optional simple transformations. These can be either applied to the actual stored data or to the coordinate LSBs inside the vector. And for example, you can choose to optionally rotate by 90. If you chose by 90, rotate by flip by top and bottom, and then flip by left and right, you would generate a rotation by 270 degrees. So we've now got to fit our stuff into our 256-bit budget. So we know there's 64 vectors in the map, so how many choices should we allow? Well, basically 4 was too small, 16 basically used up all the space, that was useless, so basically Goldilocks value was 8 choices, i.e. 3 bits per vector. Now we're storing 3 transformations, so that's another 9 bits, which left us 55 bits for the codebook, so we can store exactly 11 vectors. Now, the uniform vectors were really common, so we don't bother storing those in a codebook. We just use some dedicated indices. And then we decided to assign 3 vectors to be global. They can be accessed by any of the quadrants. And the remaining 8 were split amongst the 4 quadrants. So we wrote a very, very simple compressor. It's not my proudest bit of code. And it simply tried all 2 to the 9 possibilities of transformation. And then for a given transformation, while the codebook wasn't full, it just greedily chose one of the vectors from the set, basically the one with the fewest total check texture cases. And then once we'd filled the codebook, any leftovers were assigned to the best compatible vector in the codebook. This worked much better than expected. Very few conservative replacements were made in practice. So the blue top line basically represents the uncompressed test data, which we've basically 170, my apologies, 170 test things which we've sorted from easy to store, or the ones with the fewest numbers opaque and transparent on the left through to the ones with the most. And you can see the purple line, which is the compressed, there's very little sort of drop in savings. But you can compare that with a lossless store with the same amount of bits, which is basically 2 64 subtri opacity masks. And you can see that there's basically an 8 to 16% gain in savings. So since that worked so well, we thought we'd try something more ambitious. So basically aim for higher resolution, but without increasing the storage too significantly. So in this one, we decided to try for half a bit per region using a fixed storage of 512 bits, which is about a cache line. So that's a 32 by 32. Now, uniform, opaque, and transparent vectors are just as common. After all, it's just basically a higher resolution version of the previous one. But we do expect fewer check texture states. So our storage budget then, we decided to assign 4 bits per index. We still have the transformations per quadrant, leaving us 247 bits for the codebook. And so we have to decide how we're going to store that codebook. So unlike a 2x2, you can have all 3 cases in a 4x4 vector, but thankfully not the 43 million possibilities if you just took the naive approach. And by continuity assumption, there's actually only around about 200K, but storing those optimally with 18 bits would, well, be very unpleasant. So instead, we just simply subdivide it into 2x2s and go back to the VQ2 encoding scheme, which is 20 bits. It's simpler, slightly wasteful, but we don't care. However, we did notice that quite a lot of the cases actually only had two choices, so we can use an encoding similar to VQ2. And we also thought if we partitioned horizontally and vertically, we can get somewhere that's sort of in between the fully generic and the simpler case. And then we can combine those basically to meet the 247-bit budget. So we needed a better compressor. So we basically went back to Heckbert's median cut and get inspiration. And this one is still a greedy algorithm. It basically uses a top-down partitioning scheme. So you have a set of vectors, well, you have sets of vectors. You take one of those sets and split it into two, and basically repeatedly subdivide those into smaller and smaller sets until you have the same number of codebook entries. So there's more details in the paper, but in this particular case, we have one set there, and basically has a representative, and the error of that is 27. We split those into two smaller sets, and the combined score of that error is only 12. So how does this work with its, well, basically it's a lossier compressor, but how does it work? So it's still around 10% better than the equivalent uncompressed format, which would be a 16 by 16 at 2 bits per region. And further, the additional hardware required to decompress a 32 by 32 over a raw 16 by 16 is going to be utterly tiny, and certainly negligible compared to the rest of a ray triangle tester. So we do have some future work. Although the VQ4 compressor is more sophisticated than the predecessor, it's still a greedy algorithm. A more intelligent search, maybe with backtracking, probably should do better. We're also assuming the existence of the uniform 4x4 check texture vector, which is probably suboptimal in a lot of the cases. So we'd like to investigate ways of synthesizing some other vectors from what we've stored in the codebook. I haven't actually mentioned this previously, but the Vulkan has an opacity micromap extension, very similar to Gruen et al.'s, but they have they can have an option to store 4 different choices, but then they map that down to just 2 for cases where you're doing, say, stochastic sampling, where a jaggy edge would be totally not noticeable because you're basically scattering your samples. So we need to investigate whether we can do a hash on 3 values to just 2, probably basing it on how many of each state are in each block. And finally, can we adapt the acceleration structure traversal so that if you're, say, doing shadow maps where you don't care which is the closest, just whether you've got an opaque blocker, if you were to get a check texture case, could you just like defer it because there's a good chance you'll find an opaque or either an opaque triangle or an opaque thing a little bit later on. So in conclusion, we already knew that opacity masks could lead to savings in ray tracing with alpha tested primitives, and the higher resolutions gave a greater saving up to a point. So we're investigating using fixed rate compression for opacity maps, which allows us to have a higher resolution for the same sort of like storage budget. And we've proposed using square maps for pairs of triangles for VQ compression. And I feel what we've demonstrated that despite the compression being lossy, it is beneficial. Thank you for listening, and any questions if there's time.
Thank you for the great talk as well. We actually do have some time for questions, so please ask away. I won't throw it.
Nice talk. Is this on?
Yeah.
I mean, you basically reduced the memory footprint. Have you kind of done some measurements on how performance actually is affected because of the reduced memory footprint, because you have less cache pressure, yada yada?
No. So this will be for future hardware that will be coming along. So no, we haven't actually done that, but we kind of know what the bandwidth is for various operations being done, and we know what would happen if you were to do, we know how many cycles, okay. For example, in SOC land, we probably have to absorb 400 to 500 clock cycles of latency if you want to do something. So you need to store that stuff nearby, and we've got a small budget for our caches. we don't want to be loading too much stuff at the time. So we can see that it will be a big saving. Just don't have any sort of exact empirical values at the moment. However, I think NVIDIA had some description of the micro maps, and that was getting them a 50% saving over sort of not doing it. So basically, we can imagine the same sort of thing, but we need the compression for mobile size chips.
Okay. And one thing I didn't really get, you need to store them close together because your cache line size is bigger than your vertex data, because if you fetch something, you overfetch, and if you kind of put the opacity limit right next to each other, you kind of get everything at once. So.
Yes, that's the idea. You want to just do one burst of all your data in. You don't want to do two bursts and random disparate locations in memory. That's costly.
Okay, thank you.
In your VQ4 representation, it took 512 bits, and that's a whole cache line, you said, right?
It depends what part of the chip you're in, but yes, it's the order, yeah.
Okay, so I'm not seeing where you save the latency. If your whole cache line is full of the opacity data, then your vertex data is in a different cache line.
But you'll get a burst. So basically, you'll go out to memory and say, please read two lines of data in one go.
Okay, so you're consuming multiple cache lines through one fetch.
Yes, yes.
Thanks.
Any more questions? People want to get thrown at? Just throw it behind you and see where it lands. All right. If that's not the case, then thank you again. Okay. Thank all the speakers again.
Thank you.
Thanks again for all the speakers, and also to keep the time, disregard of the technical difficulties. So now we will move on to a coffee break, and we will meet back here at 11:10. And then we will continue with a short sponsored session and the next paper session. So see you then.
real-time ray tracing of micropolymer, hierarchical LG, Benthin et al. Our approach allows for combined like hierarchical levels of detail with hardware-accelerated ray tracing. Each user is given a text idea of HPG. There will be two tools. Spectral offsetting by Belcour et al. This paper trades a non-spectral offsetting method that, like this work, can reproduce all methods of a given color with a artist-friendly interpretation. Marking rules for and elimination by Temporal et al. Allowing the algorithm for sampling the representation based on spatial or randomized marching in the framework. Now let's wrap there will be more. New levels of detail with Deliot with new level of interpretation, where we achieve significantly better compression rates while also improving quality of previous work organization. So, conference, my name is Antialiasing. I am the Intel Research Organization.
We have a technical problem, so you go first, and then we go after. Okay. I'll just let them know.
Hello, welcome everyone. I'm Luca, and now we're going to start a session on deep learning for computer graphics. The first paper is called Generative Adversarial Shaders for Real-Time Realism and Enhancement, and Arturo Salmi is going to present it. It's a very interesting paper about using using GANs for training a bespoke shader pipeline for applying post-processing effects. It's very interesting stuff.
Do I need to do anything here, or is it? Oh, okay, perfect. Sorry. Can you guys hear me? Everything okay? Amazing. So, hi everyone. It's a pleasure for me to present for you. It's my first time at HPG. So far, it's been really good. So, yeah, let's get into it. Okay. So, I don't think it comes to as a surprise for any of you that realistic rendering is really expensive. And you see that in AAA titles as the requirements keep growing higher and higher to just run a game at comfortable interactive rates. And while this is not really an issue for a lot of games, or as long as the GPU power keeps growing, it is a very big limitation when it comes to resource constrained situations. So think about mobile GPUs, for instance, where you're not able to get you're just getting one portion of the power that you're getting with a 1080 Ti or the equivalent for AMD. So recently, image-to-image translation is starting to emerge as an alternative to do this, where essentially the idea is we get a really, really big deep neural network that learns a mapping between the output of a raster pipeline, map it to essentially realistic, photorealistic outputs, and then apply that to essentially impose visual characteristics that are typical of photorealistic outputs. So the idea is that you just get this massive network and then apply it to any arbitrary rasterized frame. So what's the problem with it now? This sounds amazing, by the way, because essentially you can just reduce the cost of your rendering pipeline, offload the entire thing to your neural network, and then be okay, this is great. It's going to be really cheap. It's going to be really fast. So what's the problem with it? There are mainly two big issues. So the first one is a neural network doesn't really understand what's the structural content of the image or what's the signal integrity properties of it. So a lot of them tend to just introduce a lot of artifacts that are extremely horrible to see, especially, no, sorry. We're trying to bit of hair, you know. Okay. So, okay, there we go. So a lot of artifacts that are essentially intolerable for especially AAA game titles. You're paying a lot of money to see these artifacts. It's not really great. And the second issue is that these networks are so big that you can't really run them at interactive rates. So even if you don't get any issues in this case, which was a really, really amazing work done by Richter and his colleagues, the model still runs half a second on an RTX 3090, which you can imagine it's pretty hefty. So there are a lot of shortcomings that come with neural network. The first one being the ability of learning so much and being so general also comes at the cost of really high computational inefficiency, because you're not using any specific in the network. The network has to start learning everything from scratch. And then you come with the other issues, so which are more related to the black box nature of it. So there's a lack of modularity that makes you understand what are the layers inside the network doing. There's a lack of interpretability and explainability, which it can be detrimental for a game artist, for instance, because you don't really have control on what you're doing or what effects you're trying to recreate. And then there's a lack of debuggability which comes with this black box approach, because the network might introduce some weird artifacts, but you don't understand where these are coming from. So having said this, what we try to do is essentially trying to define which properties do we want from an ideal image-to-image translation method. And we basically said we want that to have the same capability of learning from a large amount of data, so just like a neural network, be lightweight enough to run a real time and then run alongside any like standard like graphics workload, and then produce results that are both spatially and temporally stable at the same time. We don't want any weird artifacts on the output image. So based on this, we propose this framework that is based on lightweight, learnable post-processing shaders, and we call it generative adversarial shaders. So the idea about it is that in image-to-image translation problems, adversarial learning is like pretty much the dominant method of training. If you, of course, exclude like diffusion methods, which started recently to pop up. But the idea is that with adversarial training, you want to train like a very large generator to do this like image-to-image task, training in an adversarial way. What we do is instead of using a large neural network, we use a post-processing pipeline as our generator. And the idea here is that in each shader, which is like any standard like post-processing shader you can find in like Unity or Unreal, nothing unusual. Each of these shaders is also differentiable. So what you can do with it is like having each shader to be differentiable. You can train it in the same way as a network. So you can use backpropagation to update the weights of the shaders, and then end up with essentially a method that combines this way of like training deep neural networks with a lightweight post-processing modern shaders pipeline. So here comes the domain knowledge specific part. So we said that like neural networks are really inefficient because they are so general and they can learn so much from it. So what we did is that if we want to enhance the realism of the image, we should try and replicate different parts of the camera process of how like an image is captured. So basically what we try to do is essentially replicate, choose shaders that replicate different aspects of how a physical image is captured in a camera. So by doing this, each shader effectively would try to replicate a specific characteristics that is typical of the target data set. And you end up with a pipeline that has only like 54 parameters, which compared to like a standard image-to-image translation method, you can imagine that you're gonna have like 6 or 7 like million parameters and so on. So you already have like a massive like increase in like performance like due to the memory footprint. So the first shader that we implement is the lens blur. So the idea about it is that no cameras in the world have a perfect optic lens in any camera. So they're always gonna introduce a little bit of blur in the image. So the way that we try to replicate this effect is that we just define like a very simple like separable convolution of like size 5, and then essentially set each of the weights of the kernel to be learnable. So essentially what will happen is that the shader will learn the ideal amount of blur to add to the output frame and try to replicate what you see in the target data set. So in this example, for instance, we train the shaders on cityscapes, and you can already see, first of all, how like is already replicating a little bit how these like blur artifacts that you had, for instance, on the bushes in the background. And then you also have like this like very like neat property that comes with it, which, but I forgive the graphics people for saying this, but it sort of like acts like a very like cheap like anti-aliasing filter. So you can say already how the edges are like kind of like attenuated around the sign. So you kind of reduce a little bit the artifacts given by like the point sample geometry. So the next shader is the column mapping. So the idea with column mapping is that we want to try and replicate the color distribution of the target data set as close as possible. And the way that we do it is that we simply define like kind of completely like fully parameterized like a fine transformation. And what you end up with is essentially we're trying to replicate and learn like color distribution, brightness, saturation, contrast, and so on from the global image, from the target data set. So we're not really trying to match like specific like local details of the image, but rather we're trying to match like the global distribution characteristics of it. So you can already see for here, from instance, you have these like GTA 5 scenes taken in California, so you have like some like warm colors and stuff. And by applying like the color mapping, you get something that is already like a little bit colder in the colors, a little bit less brighter, a little bit less saturated, kind of matching like the target dataset example that you see, which are images taken actually from Germany. So sorry, that would make sense. Sorry for the German. I didn't know what it's actually really nice. But so for the bloom, I think like a lot of you guys are familiar with the bloom effect. Like it's a pretty like standard like trick used like to replicate this like bleeding effect that you get when you're trying to capture an image with a bright light source in it. Essentially what we tried to do was like trying to use that to replicate the same sort of like effect of it. And this doesn't really differ from any like bloom shader that you find in like Unreal or like Unity or in any like graphic engine really. So there you have like your 3 steps where you isolate the lights, you blur them, and then you kind of blend them together in like a really like fancy way. The only particular thing about this is that all the parameters are learnable. So instead of using a fixed threshold for the brightness value, what we do is that we use a soft threshold represented with a sigmoid. So you have like a few parameters of the sigmoid that you can use to control like this threshold depending on your target dataset. And then we also control the strength of the blurs. So these are 2 simple like Gaussian blurs that are where you learn the variance of the distribution from which you sample the weights from. And then for the light blending, we have a tone mapping curve that is like completely learnable. So you can imagine that you're gonna have like an exposure parameter and a saturation parameter that is learned on the last step. One very last thing about this is that similarly, I guess, to like how like bloom is implemented usually, is that we kind of adopted a multi-resolution approach where each resolution learns a different bloom parameter. And the idea about it is that first of all, we want like good performance, of course, because we don't want to like do multiple passes on like one resolution and then end up with something that either doesn't look nice and might be a little bit too slow. And second of all, I guess it's more to try and get like a more aesthetically pleasing effect, because if you get like different resolutions for different blooms for different resolution, you can get like sort of more descriptive bloom rather than, let's say, downsampling and passing it multiple times. And I guess it's like a lot of the problems where you see that a lot of the times bloom can be quite an annoying effect. So we try to like make it as descriptive and more aesthetically pleasing by sort of like using this approach. So as you can see from here, the shader is able to get like that bleeding effect like on the edges of the sign. So you can already see how like the light is like bleeding over a little bit of the sign. But also like on the horizon of the image, you can already see how the light of the sky like sorts of like blends over quite nicely with the trees. And then it also has this like quite neat characteristic of giving like a much closer look to the target data set compared to just applying a color mapping. And the idea here is that like with the tone mapping curve that we use at the very end of the pipeline, you get like a nice control of like the dynamics of the image by blending like different levels of brightness with it. So you maintain that global dynamic range that you have at the input, but you also get like much closer results to the target data set. The very last shader that we implemented is like synthetic noise. So if you look inside a camera, there's like a part of sensors that effectively would introduce a little bit of amount of noise into the image that you're taking. And this usually is broken down into 2 parts. So there's the sensor introduced by the readout sensors. So there's going to be a little bit of noise when the amplifiers like read the pixel values. And then there's like some noise that is introduced by the thermal sensors. So you can imagine you might have like an ADC that converts the signals to like a digital image. And that, as it's susceptible to like thermal like fluctuations and stuff, it might introduce like a little bit of noise in there as well. So the way that we modeled that is that for the pixel capture noise, we use a Poisson distribution. And for the thermal noise, we use a simple like normal distribution to introduce this noise. And the parameters that describe the distribution of the noise are also learned in order to introduce the ideal amount of noise in the image. Like, we don't want to destroy the quality of the image. We just want to introduce a little bit of detail into it in order to look a little bit more realistic. So before we get into the results, we'd like to just give you like a quick, very, very quick overview of like how we implemented this in order to optimize it. So we implemented this in OpenCL, but the idea really here is just like we want to try and minimize as much as possible like accesses to global memory. So like the algorithms itself are not really fancy. What is going to be the big bandwidth here is going to be like the way that you access your global memory. So the idea was, when possible, let's try and fuse all the kernels together and try to maximize the performance as much as we can. Okay, so I have some examples here. This is like the input frame that you've seen already in a couple of the slides. And this is one of the examples after we apply our learn pipeline. And at the bottom row, you can sort of see like the examples where it's learning from. And then there's another one here where you kind of try to get the same result. And also, as you can see, we're running this on a BTX32 MC4 at 2.8 milliseconds. Bear in mind that's a 1 teraflops per second GPU, so like it's like again like a fraction of what you can actually get from like a real GPU. And for the runtime that we get, the results are pretty good. So I've only shown you like examples from Cityscape so far, but our pipeline can really be trained on any data set that you want. So you can use like any target data set that you really want to try and recreate. So for example, here we're using Mapillary that has like sort of like more saturated, more brighter images, and you can see how the pipeline sort of like tries to recreate that. And then again, like you have like the cityscapes images that are they're kind of contradistinguished by this like lacking like bit of brightness and like low saturation. And then you can see with Kitty that is like its typical trait is like high saturation, high contrast, and you can sort of see how the pipeline can replicate that. In order to check what contribution does shader have, we tried to like break down visually what each shader is doing, and you can already tell how each shader sort of like plays an important role into like replicating one of these like different aspects of the pipeline. So you might have like for instance here in Kitty you might have like the lens blur acting a little bit more like a sharpener compared to like in the other data set as it's like it has a lot of like high frequency details and so on. Okay, so one very nice thing about our method is that without needing any retraining, any fine-tuning whatsoever, you can just take the pipeline that you've trained and apply it to any different input content. So this is like a very, very nice property that we have, because none of the other image-to-image methods can achieve the same thing. Either because they rely on metadata that might be tailored for the actual game, so they might use like G buffers that might depend on how the gamers have developed the game, but also it doesn't rely on the actual content of the image. So you kind of it basically is just modifying like RGB values. So what you have is that you can apply basically on any game, and it will work fine as long as that it will give you like pretty good results. So no need for retraining whatsoever. So we also try to do like this like a quantitative comparison between other like benchmark models. So we use basically like frames per second to just see how fast our pipeline can run. And then the KID score, which if you're not familiar with it, is a simple distribution distance metric. So the lower the score will be, the closer the images produced will be to the actual target dataset distribution. And you can already see how our model can already beat some of the models of like neural network models that actually achieve the same task. And you can see as well how much faster it is compared to like most of the neural network methods available at the moment. So one thing we have to say about the KID score, though, is not a really good reflection of the visual quality of the images. So all these models that you see here actually achieve a better KID score than us, but as you can tell, they introduce a lot of these artifacts that we were mentioning earlier, while our pipeline actually does a really good job at enhancing and changing the style of the content without introducing any of these artifacts. And again, since we don't really rely on like auxiliary metadata, we don't also get any of these like weird metadata artifacts that you might see in other methods. So for instance, in this one, you can sort of see that there was like a segmentation map over the object there, and how the network basically left an empty gap in there rather than actually like filling it up. So of course, our method also has limitations. And the main one comes actually from the property that we were describing before. So deciding to go very specific with the shaders also can limit what your network can learn in a sense, because you don't have like that nice generality that you have with like a very, very large neural network. So you're sort of limited by how specific your shaders will be. And you have this like sort of trade-off where you have to decide whether do you want to stand. So for this instance, we decided that we wanted to achieve as better computational performance as we could, while also achieving really good results. But for instance, compared to the work proposed by Richter, our method can't really introduce like additional specularity, or doesn't really like populate like hills with like foliage and stuff. But we want to try to address that in future work by taking like a hybrid approach. So combining like very lightweight shaders with what we have so far. To conclude, we have introduced this generative adversarial shaders framework. We demonstrated that it can enhance 1080p frames on a device with a mobile GPU. And we addressed like the stabilities and like the artifacts introduced by neural networks, and particularly the inefficiencies of it. And we made this like image-to-image translation task like more practical. In particular, our approach doesn't need integration cost to the developer, because it can just be applied after screen space. And it also leaves there the possibility of having like an interpretable method. So you also have the shaders, but you can already, after you've trained, an artist is free to have a look at it and say, like, I want to tweak this parameter a little bit just to modify this, like, slightly more. So it also leaves this possibility to like game developers and artists to have like a sort of interactive tool. So again, our method is easily extendable. We focused on real-time enhancement, but you can probably do the same with other tasks. So maybe if you want to do like, I don't know, cartoonization or anything similar to that, we can try to choose like more specific shaders in that sense. And in a way, there is a lot of scope on how we could exploit like neural networks to replicate less tractable effects, as we discussed earlier. So with that, I would like to finish, and thank you.
So we actually have a couple of minutes for questions, I think. Does anyone have a question? Yeah? I'll try.
Hi, nice talk. Yeah, I wonder how much this depends on how good or bad or physically correct or plausible the input is. Like, how much dependence is on the input?
So I can give you two perspectives. If you, in terms of the target data set, it would replicate, if the target data set has like really bad artifacts or anything like that, the shaders will replicate that as well. So that's the kind of thing that like comes with the realism enhancement thing, I guess. Well, like, do we really want realism in images? That's the question to the game developers. But in the part of the input pipeline, we haven't. We sort of took the same approach as other papers. So we took like the frames from GTA and tried to do the same kind of translation task. I think what we would like to address in future work, I guess, is like, what if we take a game that has less details than a AAA title and see how that can perform? I guess this would be like the very first step into that process and see how that will interact with it. Yeah.
Thank you.
Hi, nice talk. Have you played around with the order?
With the order?
Yeah, for example, putting the...
Yes. So I found sort of empirically that, for instance, for the color map and the bloom, that's the most optimal order to do that. Because I guess if you use the color mapping before, what you get is that you have a more sort of easier control of the actual target dynamics that you're applying with the bloom. For the lens blur and the noise, we actually decided to use that order from the start. And the idea is that the lens is the first thing that you have when you take an image, and the noise is really what you have in the last step, because that's what you're gonna do when you convert the image to digital. So that's how we sort of approach. And then you have the colors and the brightness in the middle of it. So yeah.
Yeah, I was thinking specifically about the color mapping and the lens blur.
Yeah.
You could imagine that the color mapping would boost some colors, and then that gets blurred, which would have a very different effect than the way you have it right now. And
yeah.
If that would be, in some cases an advantage, but I'm not sure.
Yeah, I guess if you think in a camera perspective as well, the bloom effect in reality actually happens because the sensor are overloaded with the brightness values that you're sampling. So if you're sampling the light ray, which will have your colors in there, and then you sample it from the sensor, and the sensor gets overloaded and it bleeds across the other buckets in the sensor. So maybe that would make sense as well. I think that, yeah, thinking about it. Yeah.
Thank you.
I think that's it. We ran out of time for questions. So another round of applause for...
Thank you. Thank you.
Is Kilian Arvo, right? And he's going to present the paper Minimal Convolutional Neural Networks for Temporal Anti-Aliasing. Is about using basically two sets of network, right? One to generate a sort of kernels slash effect to apply sort of kernel convolution to apply to the actual output to apply anti-aliasing with a very small kernel.
Do you hear me fine, by the way? All right. But you don't see much.
Yeah.
How do you do that? Help? It's not my computer, so never used a Mac before. It's outputting everything? Sure, you can. Does it work now? Mirror? I don't want to mirror.
Oh, I think it should be mirrored. You want to have the same output.
Yeah, but I have a presenter view here.
Right. Yeah, maybe.
I mean, I don't have the presentation on a pen, so. Ah, No.
We could transfer it somewhere. Yeah, shit.
Display connected. Extend desktop.
Oh, maybe?
Oh, well, can you just try again? No, no. Well, I don't know.
Yeah, maybe we switch.
Well, that works for me. I just need a USB something to transfer it.
Do we have a USB stick?
No.
Ah, shit.
Maybe we can do that while the next presenter goes.
Yeah, that would be an idea. We can switch it over.
Yeah.
Okay.
How about we just
yeah,
switch to the next
let's swap.
presentation? And
Yeah, and yeah, we're gonna try to fix this.
Yeah, right.
For once, technical issue, but it's a Microsoft product. But yeah, so let's welcome our two next speakers. They are going to present their work called Neural Intersection Function, and it's going to be presented by Chih-Chen Kao and Shin as well?
Shin.
Okay,
Yeah.
Shin Fujita.
Should I stand here or I just go in the middle?
What's that?
Should I stand here or I just go in the middle?
I thought you wanted to. Okay. Yeah. So, yeah, their paper is about trying to replace some parts of the ray tracing pipeline with neural networks, sort of also a bit intersecting with replacing the BVH in a way, right?
Yeah.
So, very interesting stuff. This time doesn't look like we have a problem. All right, great.
I'll come here.
So you can
I'll go in the middle.
That doesn't.
Not working. Ah, so maybe my mic is on.
I promise it's not my fault. My first time doing this, so I don't know. Maybe you can, I don't know. Yeah? Okay. Yeah? I don't know.
So it's not working now. Yeah.
Does your work? Your
No,
works?
no, it's off.
Oh, yours
probably,
is off.
yeah.
Okay, makes sense.
Yeah.
We almost got it.
He should turn on.
Or no, still no.
Working.
Okay, yeah, perfect. All right, so hello everyone. My name is Chih-Chen Kao, and we are from AMD. Yeah, thank you very much. And today I'm going to present neural intersection functions, and which is invented by me, Takahiro, and Shin. Right. And what is NIF? NIF is a novel approach to accelerate finding ray intersections, especially in Monte Carlo ray tracing, utilizing neural networks. So for today, I'm going to talk about the problems that we have in Monte Carlo ray tracing, and that motivates us to develop NIF, as well as the design philosophies of using NIF. And we're also going to talk about how to integrate NIF into the conventional ray tracing pipeline so that everybody can use it. The rest of the parts, the experimental results, and the limitation, as well as the conclusion, will be covered by Shin later. So let's jump in very quick. So multicolor ray tracing is very active research, and it has many potentials that's been known. And usually, in order to find ray intersections, usually a two-level BVH is employed. What is the two-level BVH? Conceptually, it's like this. We put objects in the scene into boxes, and we arrange them hierarchically. And then we also, for each object, it is also composed of maybe geometry primitives, such as triangles, and we also put those triangles into maybe smaller boxes and arrange them in a hierarchical way. Whenever we want to find ray intersections, we will first traverse the top level until we hit a bounding box at a node, at a leaf, and then we continue to traverse the bottom level of the BVH. And this kind of process is not good to run on GPUs. It's not effective because it is an irregular algorithm, which means during the process, we will have many branch divergence, memory access irregularities. That's not good for SIMT architectures. So overall, this one is very expensive. So that motivates us to develop NIF, this kind of approach, which is we want to replace the most irregular parts of traversing a BVH with something that comes from neural networks. And the benefit of doing this is by using neural networks, that translates the algorithm from a very irregular one into a regular program. Because inside a neural network, especially for the one that we are using, which is the multi-layer perceptron, MLP, the components or operations that is inside is mainly dense matrix multiplications, which has like regular patterns, regular memory access patterns, so that we can pre-customize or pre-optimize what kind of operation that we want to perform. So as being shown in the figure, we want to replace the bottom level BVH, which is usually the most complex part, with neural network operations. So the first thing we need to do is to formulate the problem set. So we identify the core operations of multicolor ray tracing, which is the visibility test. So given a ray like this, for example, if a ray is expressed as a position P along with a direction D, and we want to identify the function, which is the visibility test itself, to report us 0 and 1, which means if the ray is occluded or not. And then we want to design a neural network to approximate this function at the same time. We want to sorry about this one. At the same time, we want to consider how to better utilize the resource that we have. For example, the number of rays being sampled, as well as the training time, the training efficiency, and the runtime efficiency. So the challenge here is we need to tackle how the resources are used effectively, as well as how to approximate this function accurately. So our main contribution can be listed as follows, which is to improve the accuracies. Three categories, three kinds of aspects are used. The first, we need to identify the alias rays in order to let the training process much more effective. And then we need to partition the problem set itself so that we can use as minimum resources as possible. The third one is, in order to train the network effectively and cover a wide range of data sets, we want to leverage a kind of encoding method, which is called grid encoding, to discover features that can be expressed effectively. So the first thing is to identify the alias rays. So the concept of alias rays is as follows. So in here, we can see there are two rays, which is represented as P1 with a direction D1, and P2 as its origin and with a direction D2. If they will hit the same position on the objects, we want to represent them identically for the network that we want to train. How do we do that? We found that we can utilize the bounding box itself. For the bounding box that encapsulate the objects, if we move the hit point from the actual hit point to the bounding box and use that as a representation, then P1, the ray represented by P1 and P2 can be expressed identically. Yeah. So based on the observation of this bounding box, then we design the networks. So based on the position of the rays, there are two possibilities. If the rays are outside of the bounding box or they're inside. So based on this one, we designed two networks to handle different cases. The first one will be the outer network that we called. For those rays that are outside of the bounding box, that will be handled by the outer network. So starting from the hit point of the shadow rays with the AABB. Now the hit point is respect to the bounding box itself. So as you can see, P is no longer on the surface of the ground, but on the bounding box. And then we convert the original representation of rays and directions from 3D the dimensions to 2D. And I will explain the benefit of doing that. The first benefit is that we can reduce one dimension. That is obvious. The second benefit of reducing one dimension is that right now, by converting them from a 3D space to a spherical coordinate, we can use them as indexes to something else, which is our grid encoding. So the reason why we are using grid encoding here is because we found that it is very difficult if we only supply the 2D input as an input for the network for training, because sometimes the high frequency details of the scene cannot be expressed effectively, so we will lose some information. So we're thinking, how can we capture this kind of phenomenon or representation and to represent them or to express the data much more compact and expressively? So here, the grid encoding is used, and we utilize the original values, which is converted into spherical coordinate as theta and phi as indexes to the grid. Inside the grid, there are trainable feature vectors that will be retrieved when being indexed. So here, sometimes the value itself is not integer, so it will not sit directly on the cell itself. So here, the bilinear interpolation method is being used to get the actual trainable features vectors. For the inner network, that will be very similar, but instead, now we need to consider if the object itself is concave. If the object itself is concave, there will be many possibilities of the hit point inside the bounding box. Then again, since we are considered the distance from the hit point to from the origin to the hit point, we want to represent that compactly and expressively. So we also utilize R, the distance from the origin to the hit point, as an index to an 1D grid as well. So in the 1D grid, it's very similar concept as in the outer network. It stores a trainable feature vectors that can be retrieved later on. So this is the overview of the network. As you can see from the left-hand side, for each object, we will have a bounding box. And based on where the position of the ray is, it will have two type of situations. For example, in here, for the outer network, we're utilizing a direction grid and a position grid. And inside those grids stores training factors. Once we retrieve those training factors, we concatenate them to form the actual input to be trained in the neural network. And during the backpropagation process, those trainable features stored inside the vectors will also be trained and updated correspondingly. The inner network is very similar, except that it incorporates another grid, another 1D grid, which is the distance grid here as well. And this is the results. No, this is the ground truth of this method. So in here, this thing, you can see there are like 3 objects, 1 bunny and 2 teapots. And this thing is being rendered by image-based lighting. And this is the result of NIF. As you can see here, I want to tell you that this thing is only being trained for 20 samples per iterations per frame, 20 frames, 20 iterations per frame, sorry. Yeah, but as you can see, for this small amount of training iterations, most of the details can be preserved. And you can also see where those results are coming from. For example, the blue one is coming from it's being inferred by the inner network, and the red one is from the outer network. Yeah, and this method will not be very useful if we cannot use it. So here I want to explain how this one can be easily integrated into the conventional ray tracing pipeline. So starting from the camera itself, so we can still cast the primary ray of the camera as usual. Then we cast the shadow rays whenever we hit something, right? And then we start to traverse the top level BVH until we hit the node on the leaf. And then one thing that needs to be taken care of is now we store the input data instead of traversing the bottom level. So we will have after this process we will have a series of trainable, the data that we want to invert. For example, the directions and the position of the grid, of the rays, and then we convert to the grid indexes as explained before, and then we execute NIF. So that will include to look up the indexes in the grid to retrieve the trainable factors, and then we use those trainable factors to infer the MLP. Yeah, so this is the actual architecture in details. So here, as I explained, for the outer network, there are two grids, one for directions and positions, and they are in 255 square as a resolution. And for each one, we will retrieve trainable feature vectors. Here is, both of them are 3D, so by concatenation, there will be 6D. And then we supply this one to our MLPs. The MLP itself contains 2 hidden layers, which has 64 each nodes. And then at the end of that, there is a signal activation function, which reports and probabilities between 0 and 1. And for inner network, the architecture itself is very similar, except that there are more layers, but each one has reduced number of nodes, and the resolution of the grid is smaller. Yeah. And the rest of the part will be handled by Xin. Thank you.
Hello? Yeah, can you hear me? Okay. Thanks. Yeah, from here, so as Chih-Chen said, so I'm Shen, so I'm presenting here. So using these networks in the previous slide, we evaluated the performance of NIF compared with the BBH-based implementation. So we implemented them using C++ and HIP for the GPU programming language, and we evaluated it by rendering images with Full HD on the AMD Radeon 7900 XTX GPU. And also we use some support on this GPU for the optimization of this implementation. So right there, for the BBH-based implementation, it uses state-of-the-art SA HPBH builder with the support of the hardware ray tracing cores. And also neural network execution on NIF uses the WMMA, so wave matrix multiple accumulation instruction. This graph shows the comparison of the secondary recasting time between NIF and the BBH-based implementation, and we evaluated them with 9 scenes. The top colored bar shows the NIF performance, and the bottom white bar shows the BBH-based performances. And the red bar contains top-level BBH traversal and the input data collection. And the blue and the yellow ones indicate the feature vector lookups from the grid encoding. And the green and the purple ones are neural network inference times for the outer network and the inner network, respectively. And also seeing this comparison, the performance improvement varies depending on the scene. But for the best cases, this one, so NIF reduces the secondary ray casting time about by 35% compared to the BBH-based implementation. So in this high statute scene. But what's the factor deciding this performance gain of NIF? So then, let's see it a bit further. These two figures show the NIF's ray casting time arranged by the number of polygons in the scene and the number of rays processed by NIF. So seeing the left figure, we can find that NIF has nothing to do with the number of polygons in the model. However, seeing the right figure, we can find it's almost linear to the number of rays processed by NIF. So therefore, because NIF's computational cost is not proportional to the model complexity like these images shows, then NIF is more effective when it's applied to the complex geometries. And if it's applying NIF to the model with a low complexity, it could not gain much benefit from it. Again, seeing this comparison, we can see this nature by focusing on these two scenes, tie statue and tie statue row scenes. So these scenes look like these. So although they look almost same, the number of polygons in this tie statue model is different. On the left tie statue scene, so it contains 10 million polygons in this model, but in the right tie statue row scene, it contains just about 0.5 million. Polygon in this tie statue model. So because of this model complexity difference, the BVH ray cast time takes about 50% more than that on the left such a model due to the bottom level BVH traversal. And on the other hand, NIF only takes about almost same time, about 260 microseconds for both scenes. So as a result, we can see applying NIF to more complex model as much more effective, as we can see with this speed up result in the bottom row. So the left scene shows a 1.5 speed up comparing to the the right BVH-based model. And from here, we will show rendered images for these two scenes, statues A and statues B, which show about 40% performance improvement. And you can find more rendered images for other scenes in our paper and the supplemental document. So please check them if you're interested in. So first, this is the scene of statues A. So it's rendered with a BVH-based ray tracing. And this is NIF. Probably it's hard to see here, but yeah, this one is NIF. And this is rendered with ray tracing again. And this is NIF. Yeah, and yeah, another scene statues B. So this is rendered with BVH ray tracing. And this is NIF. So, and again, so this is ray tracing. So this is NIF. So probably it's on this screen, so you can't find any difference on this. So please check the letters on our paper to further detail. But yeah, actually, so there is some difference, but the rendered image using NIF still preserves the image quality while improving the performance here. Additionally, we demonstrate NIF can also accelerate ray casting in a more complex scene, and can be used in one unified rendering framework. We test NIF in this scene where 6 complex models are placed in the bistro scene. As explained before, applying NIF to simple objects is not beneficial. So in this test, we execute NIF only for the model with which have more than 100,000 triangles. And for other simpler models, so we just traverse the bottom level BVHs as usual. So even in this case, so NIF reduced the secondary ray casting time about 15% while preserving the image quality. So again, I will show there some comparing result, ray tracing and NIF. This one is ray tracing result, and this one is NIF. So again, so this one is ray tracing, and this one is NIF. So actually, again, so it's hard to see on this screen the difference, but yeah. We can say the difference is relatively small, and yeah, if seeing only these images to you, we believe you can't make a decision that this is rendered with our NIF approach. So you can't, yeah. I think so, yeah. Sorry. Anyway, so yeah. So this is a NIF rendered image, and 2 shows the applicability of NIF to other types of rays. We also tested to apply NIF to primary ray casting. And yeah, in this scenario, the input to the network are same as before. But for the output, so this time instead of inferring the visibility, the network outputs shading normal and the depth from camera, which is a 4-dimensional vectors. In this application, errors of NIF directly result in visible artifact, and the accuracy is honestly still not enough compared to the BVH ray casting in this case. But yeah, let's see some results here. So this shows the result with the Csefalvay model. Left one is using the ray tracing, BVH-based ray tracing, and the middle one is the result with our method NIF. In this simple case, so it seems NIF shows a kind of good result. And on the other hand, seeing this result with Dragon model, we can see some degradation on the result with NIF. Here, especially in shading normal, like this. So left is a ray tracing result, and right is a NIF result. So yeah, actually, so improving accuracy is one of our future work. So yeah, finally, let's discuss with the limitation of our approach here. So first, now in our approach is we focus on just the visibility of the secondary ray. although we have shown some application to the primary ray casting. So extension to other types of rays with improved accuracy, such as more deeper rays of shadow rays, is our interesting future work. Also, NIF is trained only with the rays based on the current viewport. So, so we need to train NIF again in order to achieve better accuracy for other viewports or other light sources. So again, so extension to dynamic scene, extension to animation also remains our future work here. And this is kind of not a limitation, but yeah, actually, so our current implementation of NIF can be further optimized by reducing redundancy. So for example, like this image, so we're executing NIF for this pink ray, so this 2 times for the 2 hit point red and green. And but yeah, we don't need to, if the intersection point is found on the red hit point, then we don't need to execute anymore for this pink ray for the green hit point here, because its intersection point is already found. So like this, so we can further optimize it for our implementation. Then to conclude our research here, so we introduced a novel method using MLP to accelerate the ray casting time, so called the neural intersection function. It works as an alternative to the bottom level BVH traversal and can be integrated into the existing ray tracing pipeline, which has been never shown before. We also shown NIF can represent geometry with sufficient accuracy with improved performance. In order to achieve good result, we propose to use 2 different networks, outer and the inner network, and the specialized input parameterization for grid encoding. And also our experiment demonstrated NIF reduced the secondary ray casting time by about up to 35% while preserving the image quality. So yeah, finally, that's our contribution, but finally, so the application of neural network-based methodology in computer graphics area is a kind of emerging technology. So, however, the efficient integration of the neural network into the conventional ray tracing pipeline is requires more further explanation. So we hope our research is a kind of starting point, and yeah, we inspired more future research in this direction. Yeah, that's all. Thanks for watching, and yeah, any question?
All right, so we have a couple of minutes for a couple of questions, I guess, or maybe just one.
Very nice talk. Do you have a table on memory consumption where you basically compare adding up the 2 neural networks versus the, let's say, compressed BVH or something like that? Or can you just tell me, is there a factor in between?
Sorry, I couldn't hear. Can you understand that? Can you hear the question?
Oh, sorry. So
yeah.
Should I repeat? Sorry about that.
Yep.
So it's all about memory consumption, right? Do you have a table where you compare the memory consumption of the 2 neural networks, right, versus, let's say, the compressed BVH that you use? Do you have such a table?
Yes, we do have such a table, and I think I can't remember the exact number, but I think if we utilize the grid itself, the grid is in constant memory.
Yeah.
So that we need, for example, for the outer network, we only need 2 type of grids, one for position and direction, and depends on the resolution that we configured, that will cost us constant memory.
And how big in bytes is the, let's say, the neural networks?
I think for the grid, right, for the grid encoding, and we are utilizing 3 dimensions, and the one of the elements inside the trainable vector is like 32 bytes. So it's like 32 bytes times 3 times, depends on the resolution, is 255 square.
And also, additionally, so we need more memory to further the weight of the neural network. But the neural network is shared for the all objects, so it's a constant for the. So it's kind of small.
Okay, got it. Thank you.
So single object is represented around like a 300 kilobyte. That's it. So even like a 100, like a 10 million like polygons, it's compressed into 300 kilobyte. So it's very like aggressive compression.
Yeah, thanks for additional answer.
Very interesting talk. Is there a restriction on the execution of the neural network that needs to be in like wavefronts in order to utilize like the equivalent of tensor cores, or?
No, so our implementation is not to utilize that tensor core or something like that. So for the hardware implementation to accelerate the neural network, so yeah.
All right.
But for training, we do utilize the wave MMA.
Yeah.
To speed up the matrix multiplications and accumulation.
So there's no acceleration at inference.
Mm-hmm.
Okay.
Yeah. We do, but yeah, it's just a software implementation, so so it's not to utilize any hardware core, hardware accelerator for the neural network.
Okay, thank you.
Yeah.
I think this will be it. Another round of applause.
Okay.
And now we're going to try again with Kilian.
Hello? Yeah, great. So, computers don't like me today.
Try directly on the HTML.
Yep. Sure, I mean, great. I promise next time I'll bring my own computer. All right, so we're here for temporal anti-aliasing with neural networks, obviously. Work that I did at the KIT Institute in Germany with Max and Carsten. You know aliasing, what we get when we do rasterization or ray tracing, the jaggies, they're everywhere they're always there when we are doing rendering, which means that anti-aliasing is also mostly everywhere. So anti-aliasing is common, and we want to have a good one. And we know that there is more data to be gained in the frames that we've just rendered. We just spent budget on it. So previous frame are more data, but some of it is good data. And temporal anti-aliasing has a problem, which is you need to get rid of the bad data and keep only the good one. And this is difficult. And at some point, temporal anti-aliasing becomes some of a college of strategy, which are somehow a little arbitrary at some point. And they do get some correct results, and it's decent, but it feels like it's asking more questions than it's actually giving a good answer to the initial problem. So we had the idea that deep learning can just replace all the arbitrary stuff that we're doing and keep the good stuff that we have been doing for a while. So let's just see the pipelines real quick so that we can be on the same page. So on the left, you have the input, you have your anti-aliasing algorithm, and then you have an output. Simple enough. Then for temporal anti-aliasing, you need more frames. So you have a bunch of frames, you use your temporal anti-aliasing algorithm, and you get an output. And usually, to use this data correctly, because of course your camera has moved in between, you use motion vectors. So you have a motion vector that tells you how to go from each of these frames to another. And what you do is you move the previous pixels to the position indicated by the motion vectors, which gives you a new frame that is hopefully more interesting and more useful than the previous one. But that is still a lot of data. You don't use that in runtime, right? That's a lot of buffers, and you probably want to add the depth somewhere. That's too many buffers. So what we usually do, this is good for training, but for inference time, for runtime, it's not really good. So we instead use another approach. We take the current frame, which is the aliased frame, and the previous frame that we have already processed, and the motion vectors between the two. Then the temporal anti-aliasing algorithm produces its output, which is fed back to the next iteration. It's much lighter, much more suitable for runtime. But I'm sure you already know most of this, just for us to be on the same page. So let's see what we have hidden in this TAA blue box. So, as I said, we have our motion vector and our previous output, which we will project. This is one part of our input, which also contains the current frame and the depth. And we also feed it a hidden state. So it's basically a storage unit for the network to remember things and to communicate to the next iteration. All this becomes the input, which has the size of your frame, plus so the 3 channels of the input RGB, the depth, the reprojected RGB, and n layers of the hidden state. We did a few experiments that you can see in the paper, where we tried different hidden state channels count, and 5 we found was a good amount, and it depends a lot on how much input, different kinds of inputs you have. If you want to add more than input RGB, depth, and reprojected, if you add some more, it's also better to have more hidden state. So the hidden state is produced by our network in this way. So you have here the convolutional neural networks. So 3 by 3 is the size of the kernel, and 6 here is the size of the output of the kernel, so it's number of channels. This number also, we tried a bunch of different numbers, and 6 is on the lower end, and 12 is above 12. We didn't see any more improvement in quality. So we have these 3 main CNNs, and it branches out here with just one that allows the network to remember things. Of course, networks don't remember things, but it stores at least some data for later, and we're going to talk about what's inside this hidden state. So these are very dark. But you see on the right, maybe, basically the networks comes up with this. We didn't tell it to do anything specific. This is what it chooses to remember for the next frame. And I've looked at a lot of different ones. They are very different. And they are basically all variations of common filters, like, thank you, that's very nice. Like edge detection filters, you have dilation filters, you have thresholds, and it's a combination of all of these. So yeah, I've indicated at the bottom that we use 5 channels of these, and we did not notice any improvement beyond that. So let's go back to our architecture. The core of our technique is the kernel prediction. So we have a 5 by 5 CNN again, but this time with a 50-layer output. So this is pretty big. And this is because it's 2 kernels of 5 by 5, basically. We are trying to predict 2 5 by 5 kernels. So we apply then these 2 5 by 5 kernels to our current frame, the aliased one, and our reprojected previous output frame. So you can see here how we do that. It's basically just an operation where each pixel gets its own kernel, and we just apply the kernels on the image. Very simple. We sum them, and that's our output. We experimented with more kernels and different variants of the current frame, reprojected, etc. For instance, we also tried with the non-reprojected previous frame, but this actually led to artifacts. And you can think, why are we doing this? This sounds kind of odd, like a convoluted way to get what you want. But one very big benefit is the network can absolutely not dream up things, because it's only using data that's already there somewhere. And this is a big advantage because, as we know, networks tend to dream up things. Also, this is the configuration that yielded the best bang for your buck, basically, in terms of memory and computing cost. So there's one thing we didn't talk about yet. It's that we have different sets of weights for our network. So each layer basically is a learnable set of weights. And we rotate them because we have our renderer that also has something that rotates. It's the Halton sequence in your, basically it's where you aim your ray, when you're ray tracing, you aim your ray inside the pixel somewhere, and it's better to rotate this place so that you can have more data and more variety in your data. And we noticed that there is a significant improvement when we also match this strategy with our kernel prediction. And you can see it here. On the left, we have the exact same network, but one has no rotating jitter sets of weights, and on the right, you do. So you can see a significant improvement there. We have also more variants of which layers we rotate, and you can see that in our paper. So we have our architecture now. Let's see the training data. We have 3 scenes, from the left to right: cafeteria, stairs, and seaside living room. It's more or less realistic camera path with faster, slower movement, and sometimes going through walls, as users often do. So we have a bit more than 500 frames. It's a fairly small resolution, 640 by 480. It's because we need a reference, and the reference is basically we render a very big frame and we downsample it. And so I'll tell you about this a bit later. For each scene, we have a supplemental video, which covers all the comparisons, if you are interested. So during the training, we have randomized patches of 128 by 128 pixels. We have batches of 24, so it's just enough to fill our NVIDIA Titan V. And we use the non-stateful approach, so the big one. This is because it's faster, basically, to train using the non-stateful approach. So the one with all the frames at once and all the motion vectors. We also perform data augmentation. So here we use only channel switching. So it's basically we rotate each channel. RGB becomes BRG or whatever. And it's additional entropy for the network. Even without the data augmentation, we have more than 80 million training samples, so arguably we can't define that as an epoch. So we had to define it arbitrarily, and we decided that 1,600 patches processed, it's about 2 minutes, and that's our epoch. We usually take 400 epochs for research and validating networks, etc., and 800 for presenting final results. So yeah, how did we get the training done? Of course, we need the reference, and as I said, since we have only reference from 2560 by 1920, we didn't want to resize it too big, otherwise we would not have a great reference. If we would have 8K, we could probably go 1080p. But it works very well already, so it seems like it's not necessary. I'm sure we can go even higher in quality if we have a better, higher resolution reference. We downsample it. We resize it, sorry, with this filter here that you can see that I shamelessly stole from Wikipedia. And to train, we need an estimate of how well the network performed. This is indicated by losses, and all our losses are pixel-wise, so they work on individual pixels. We have first the reference loss, how different the output is from the reference, the gradient loss, which is the same, but for the gradient in x and y directions, and the temporal loss, which is arguably the most interesting one. It's how much there is temporal change between the output, the current frame, and the next frame, compared to how much there is a difference between the reference current frame and next frame. How are these losses exactly computed? It's very simple. It's output minus reference, a gradient on x of output minus gradient on x of reference, etc. And you add the gradient in y. And the temporal loss is the interesting one again. So we define the difference between one frame and the next. We define it as a temporal gradient. And you simply do the gradient of the output minus the gradient of the reference. This is by far the most important loss. And the thing is, they have different ranges. So if you compute a gradient, it's not going to have the same range as a simple difference between two images. So we need a coefficient for each loss. That's what we use to adjust the relative importance of each of these losses. And we also use a mask, which allows us to target specifically the regions that have more aliasing. So you can see how we do that here. It's just a simple operation. You can find more details of that in the paper. So we also have a coefficient to select more aggressively the aliased versions, the aliased regions. We found that it doesn't matter that much, and 0.65, so it's a ratio, it's not 0.5, which would be 50-50. We favor a little bit the aliased regions, but apparently it works well on anyway, except if you go for very high or low values. So what are these losses actually doing? It's important because you don't need a loss that doesn't do anything for sure. So these are the most important things that you have to care about when you're training the network, such kind of networks at least. It's how you tell the network if it did a good job. And the reference loss, we notice it increases frame by frame quality, but it has no impact on how well it does temporally, very little at least. The gradient loss helps with a little better convergence. We gain around 20, 50 epochs in the convergence time. And finally, the temporal loss, it dramatically improves the temporal stability. So let's see how that works. So here you see an example with low temporal loss, and you see it flickers a bit all around. And here you have an example with high temporal loss. And you can see it's way smoother. It still wobbles a little bit. I mean, you have to remember the input is very noisy, but it's significantly better. I can still show you maybe the previous one again. So this is how much it flickers. And the next. So of course, it's a situation where you have a lot of disocclusions and occlusions, so you still have some amount of it. It's significantly attenuated here. So that was the point for carefully choosing your losses. Now let's see our results. So again, we only using 640 by 480, and we are comparing against variance clipping TAA, and you can see all the videos in the supplemental again. So we just have some images. So on the left you can see the reference, and on the right the input. So they have been resized higher so that you can see it well here. So you can still see the input is quite aggressively aliased. And here's our output on the right. And here's VCTAA. And you can notice there's a few artifacts that appear because this frame is actually taken during a motion, and this is a lot of ghosting that you see there. And here's our output against VCTAA. And maybe you're more interested in looking at close-ups. So here on the left you can see ours and VCTAA just next. So hopefully you can see how the shadows and at least the light in between the shadows is correctly resolved by our technique. And VCTAA struggles there. and it otherwise struggles on the lights. You can see that the red has almost disappeared on the behind the railing, where it's still a little present, and the white of the light is still quite present. So obviously I'm talking about temporal anti-aliasing and I'm not showing you a video, so that's annoying, but it's coming soon. But first we're going to talk about timings and our terrible Catmull-Raman interpolation that we're performing. That's the thing that allows you to reproject. It did not exist in TensorFlow, so we have to code it ourselves, and all of this was coded on TensorFlow and the Python implementation. It allowed us to have a lot of variations of networks. But then we had to sacrifice a lot of performance for that. The column mix operation was also performed by us, and it's a CUDA kernel would dramatically 10x this thing quite easily. And the Catmull-Raman interpolation, I'm pretty sure most of you know that there is a brilliant new way to compute it with only 4 bilinear fetches, which is really great. And you can definitely get 2 orders of magnitude on this reprojection. But for what results? So I'm going to show you a video of this lampshade there, as you can see on the top of the table, zoomed in so that you can clearly see how the network resolves the lampshade, because it's a thin geometry, which is relatively far away. It's hard to resolve because it's at the limit of how the pixel size. And here it is. So I'm going to show you a few times because it's a very short extract. You can see on the bottom the target. So it resolves, of course, very well. On the top right, the VCTAA, which is quite blurry. And we can see that we noticeably resolve the lampshade, but also the slats in behind, the thing that blocks the sun. They are significantly less aliased than the VCTAA version. And you can obviously see this and significantly more in our supplemental and our paper. So thank you for your attention.
I think we still have a few minutes, or yeah? Okay, so let's do a couple of questions. I don't know where is the cube. Where's the cube? Oh, all right. So does anyone have a question?
Hello. Have you tried to, for the 5x5, to use like a separable one instead? So like a 5x1 and then 1x5?
You mean for performance?
Yeah.
I know that the separable kernels come with the restriction of the rank of your operation. And to be honest, I didn't try. But I was wondering that it would probably lead to a loss of generality in the network. But that would be a good thing to try, because it's definitely significantly faster, especially for the scaling. But just as I said, here, the scaling is not too much of an issue here. So, of course, for our terrible Catmull-Raman interpolation.
Thank you.
Any other question? Oh, I see one there. You can try. Want to try? Yeah. I can do otherwise. Eh? I trained. Yeah.
Oh,
awesome.
Good for all. Hi, thanks. So I have a question. So in your results, you only compare it to one other method, which is, I think, not learning based. Did you maybe internally, like in your research group, also compare it to, for example, DLSS and XESS, so other AI?
Yeah, so it's interesting because these methods are doing super sampling, which is slightly different. So they're taking a lower resolution frame and expanding it. So of course, if you resize it again, it's kind of an anti-aliasing. But due to many constraints that we had with our dataset and how we built the network, we had trouble implementing it. So it would have been a very good comparison for sure, and maybe even more interesting on DLAA, which is the NVIDIA equivalent.
Hi, have you tried this with particle effects or things that have transparency, no depth?
You mean small dots that move around very quickly?
Glass or anything?
Yeah, so this kind of method relies on motion vectors. And if you can get good motion vectors for that, it's going to work. If you're not getting good motion vectors, it's not going to work. And it's mostly down to that. And getting good motion vectors is definitely still an area of research.
Thanks.
That's it. Maybe I can have a last question. Yeah? Well, no, sorry. No, so I was wondering if you also looked into dimensionality reduction, because you basically always keep the same dimension of your input throughout, right? So you never decrease the 2D dimension, and you also not increase the channel dimension, which is kind of common when you see traditional CNNs, also like UNets or any generative one, tend to do this dimensionality reduction and then upscaling it again.
So you're asking if we tried that? Yeah, we definitely tried it. And what we mostly noticed is that it introduces a lot of a dependency in the network, because while you're resizing and then processing on other sized inputs, it's a lot of time. It's necessarily a sequential algorithm that you're doing there, and that's quite bad for performance. So we tried it. We didn't get through to get, first of all, good results. The results were not super satisfactory. And we didn't notice a very big interest there. Maybe someone can implement it better than us, though.
All right. Oh, interesting. Yeah, I think that's it. Another round of applause for Killian. But don't leave yet. We now have our sponsor session coming up.
That's right. We're just quickly doing an Intel sponsor session, and then you guys can go for lunch. So that's coming right up. Thank you.
Hello, HPG conference. My name is Anisotropic. I'm with Intel Graphics Research Organization. Intel is the year-over-the-year sponsor of HPG, as we value every opportunity to broadcast knowledge within the research community, support best computer graphics papers and their authors. This year at HPG, we have 3 great talks you don't want to miss that are coming up right after. Real-time glint rendering by Thomas Deliot et al., a new method to simulate the appearance of glittery surface that runs in real time with stable performances on desktop PCs. Important sampling GGX normals by Jonathan Dupuy et al., a novel algorithm to evaluate GGX distribution. It is simpler than the state-of-the-art and leads to faster performance, thereby offering systematic speedups. Real-time ray tracing of micropoly geometry with hierarchical LOD by Benthin et al. Our approach allows for combining nanite-like hierarchical levels of detail with hardware-accelerated ray tracing. EGSR is coming up next right after HPG, and there will be 2 talks. Spectral upsampling by Laurent Belcour et al. This paper introduces a novel spectral upsampling method that, unlike previous work, can reproduce all metamers of a given color with an artist-friendly parameterization. Markov chain mixture models for real-time direct illumination by Dieter et al., a lightweight guiding algorithm for sampling direct illumination based on spatio-temporal randomized Markov chain mixture model. In August at SIGGRAPH there will be more. Neural levels of detail by Philippe Weyer et al. With neural level of detail representation, where we achieve significantly better compression rates while also improving quality over previous work at interactive to real-time frame rates. Minimalist deterministic diffusion model by Eric Heitz et al. The diffusion model that we obtain is pretty much equivalent to the existing ones, but the whole point is the derivation that we believe is simpler. To democratize and accelerate research and development of real-time path tracing across academia and industry, we aim to open source our internal research framework with many bleeding-edge techniques. At the same time, we will be releasing a real-time path tracing demo created using our open source framework to challenge the assumption that real-time path tracing requires powerful and expensive high-end GPUs. On top of that, we will be giving the talk in Advances in Real-Time Rendering in 3D Graphics and Games, well-known course at SIGGRAPH. In this talk, we explore the new shortest path to high visual detail using real-time path tracing on low-end and mid-range GPUs, highlighting both interesting challenges as well as discussing where feasibility is closer than commonly believed. Based on explorations in our path tracing research framework, our topics include rendering high-detail scenes in order of trillion triangles, managing dynamic scene updates, as well as handling severe noise and aliasing with robust temporal accumulation, upsampling, and denoising. Finally, we will discuss the opportunities for light transport levels of detail, neural representations, and other promising components to further advance real-time performance. Make sure to tune in to the upcoming Intel Graphics research announcements. Thank you for listening and enjoy HPG.
All right. Good afternoon, everyone. Ready for the afternoon program we are after a very nice lunch. I'm replacing Philip Sluselek because he couldn't make it today. So a bit of improvisation on my end, but I think we should be fine. So we have a number of interesting papers coming up being presented in the session on cloud-based rendering and distributed rendering. And before we actually get started with that, I have one request to share with you, because downstairs Andrew Gerard is still sitting on a very large number of Cornell boxes, and some of those are maybe your property. So if that is the case, then please pick up one of those and make him very happy. Otherwise he needs to bring it all back with him, which is not good. So on with the session for this afternoon. For the next 100 minutes there will be 4 papers, and the very first one that we will be listening to is data parallel multi-GPU path tracing using ray queue cycling, which is all about the efficient path tracing on a multi-GPU system of very complex scenes using a clever work propagation system. And this will not be presented by Inge Walt. I mean, Inge Walt also couldn't make it, so but luckily Stefan Zelman will take over. So the floor is yours.
Yes, thank you. Can you hear me? Yeah, I hope I do a good job stepping in for Inge, who unfortunately cannot be here today. Yeah, this talk is going to be about data parallel path tracing. Let me first give you a brief overview of what we're going to talk about. We're going to talk about data parallel path tracing, and in particular multi-GPU path tracing. We're going to talk a little bit about what the status quo in this regard currently is versus what we really want, how we really want to do this. I'll explain this method called that we adopt ray queue cycling. I'll present the basic idea. Then have a little time to explain some of the optimizations that we applied. Then I'll wrap it up for showing some results and so on. Yeah, and the talks yesterday, and some of the talks we already heard what the data looks like nowadays. Like, we learned that data has become much larger. And this is to do with several factors, for example, with tooling. So for artists and for efforts, it's much simpler to create something small and then replicate it a bunch of times so that you have something really big. And there are other factors that also facilitate this, like, for example, the fact that many rendering pipelines nowadays are based on ray tracing, where the complexity is no longer bound by the geometry, or is logarithmically bound with the geometry. So that means adding twice as much geometry doesn't make you twice as slow. So that means that big scenes are nowadays even commonplace in games. Yeah, let's talk a little bit about, now that we know what the data looks like, let's talk a little bit about what the hardware looks like when you're not particularly in games, but when you're, for example, in production, or when you're doing large-scale scientific visualization. Hardware that you might resort to might, for example, be multi-GPU servers, for example, in the Amazon cloud, or on a supercomputer. And the kind of hardware that we see a lot nowadays are multi-GPU systems, where the multi-GPUs are connected, usually using PCI Express, but quite often actually using some vendor-specific interconnects, such as NVLink, which has like extremely high bandwidth. So, and these multi-GPU systems, for example, when you take like a typical cloud-based system and you do the math, you will find that memory actually compounds a lot. You can easily, like on a single system, have hundreds of gigabytes of memory available. So yeah, when you look at the data, I said the data is relatively big usually, but to really saturate these 100 gigabytes of your single multi-GPU system, you need like really big data. And yeah, when you resort to like those hero data sets from NASA, for example, who have their NASA Mars lander data, they're really huge and they might exceed that. But models of the size of hundreds of gigabytes are actually not that easy to get a hold of. So in terms of what we want to use those systems. We want to use them well. We want to use GPUs, obviously, because they have hardware ray tracing. And even if we don't have hardware ray tracing because we're in an architecture that is more optimized, for example, towards neural nets or something like that, we still want to use optics because we don't want to go through all the hoops implementing BVH intersections and stuff like that. But what we also want is, we want to take that single system and want to ideally use it as though it was a single GPU. And if you take a look at the state-of-the-art in data parallel rendering, for example, Ingo's paper from last year's HPG, you will find that they have like very sophisticated partitioning algorithms that spatially or using BVHs partition the data and then distribute them to multiple nodes, and then quite often use MPI, which adds extra layers of complexity. And we actually don't want all this. What we really want is we want to use the system as though it was a single GPU or a single system. And therefore, we came up with this idea that we called array queue cycling. And the idea is really simple. What we came up with is, what if we take the data and just think triangle soup, and then chop the data into pieces so that we use as few GPUs as possible, and then generate rays on each GPU, cycle those rays through that in the end, every GPU has traced every ray, and then return it to the GPU that is responsible for shading, and then perform shading there. So this is obviously correct, like when the data is distributed among the GPUs, and every GPU is processed all the rays, and we updated hit records accordingly, then in the end, we'll have something valid, and we'll be like back on the GPU we started at, we can perform shading there. But it's obviously slow, right? Because sending rays over and over consumes a lot of bandwidth. And this is the question that we asked ourselves, is it really? Or is it not? Let's talk a little bit more detail how we implemented this. So disclaimer, we implemented this actually to find out how slow it really is. And this is what we did. We took the data, and I'll talk a little bit more about data distribution in a little bit, and try to pack it on as few GPUs as possible. And then we have a working set of n GPUs that have data and memory, and then we have on each GPU we generate 1/n of the primary rays. So and then we trace on each GPU we trace those primary rays, record the hit information, and store the hit records along with the rays. And when all the GPUs are finished, we take the rays, including hit records, and cycle to the next GPU. GPU 0 passes its rays and hit records to GPU 1, GPU 1 to 2, and we make this form a ring. And then we cycle n times, and then we are back at the GPU where the cycle started. And then each GPU has traced all the rays, and the information which objects were hit is back at the GPU that dispatched these rays, and then we perform shading. So if we have like a path tracer or something that like that, we repeat that multiple times, like for each bounce that we have. And then in the end, we have a distributed results, like an sRGB result, and that we send back to GPU 0 or whichever GPU is responsible for displaying the image. So that's the idea. It's as simple as it gets. Let's talk a little bit about details. The first and probably most important detail is how to partition the data. And this is also what the big advantage of this method is that partitioning is most simple. I earlier said triangle soup. But that's not really what the data looks like. When you take a look at, like, for example, the Moana Island or some data like this, the data looks more like you have meshes, and then each mesh is associated with a material, and it's maybe a texture or maybe multiple textures. And then you have objects that are composed of meshes. Think, for example, a tree, and the tree is composed of a trunk mesh and of a leaf mesh, and they together form objects. And then you have instances. So you have your Moana Island, and you have like a bunch of trees here, and you have a bunch of trees there, and they're all the same tree, but they're multiplied via instancing. So like a traditional object space partitioner, what would it do? They would just maybe place a split plane in the middle, and then take all the instances to the left, put them on GPU 0, and would take all the instances on the right, put them on GPU 1. But then the problem is you also have to replicate the object, right? So And that turns out that can go out of hand real quick because you have to replicate the objects, and that's not really what you want to do. What's the alternative to this? The alternative to this is that you directly place the objects on each GPU. And as I said, we can partition however we want. The important bit is we cycle all the arrays through all the GPUs. And that allows us to put the data wherever we want. So with this degree of freedom, what you really want is you want to distribute the object. And then you put all the instances where the objects are. This, of course, gives you an awful spatial distribution, but it doesn't matter. Like, you trace array into that, and you maybe have a BVH with lots of empty space, but it doesn't matter, because tracing arrays nowadays is extremely fast. And that's the whole point here. How you partition the data doesn't matter. Like, you just put objects where you want to put objects, and you don't have to do any fancy splitting. You don't even have to touch individual triangles or do things with sweep planes or stuff like that. You just take the data. Like when it's triangle soup, it's extremely simple, or when you have like structured volumes or something like that, it's extremely simple. But even in this case, where you have this complex data with multiple instances, with meshes and objects, it's still extremely simple. There's the first incarnation of what we had. Just did a round-robin assignment. It turns out that can become quite bad, actually, when you have like a bunch of really large objects. Like, think the Moana Island ocean surface, and then you have like maybe 2 ocean surfaces, and then you equivalently have like 2 GPUs fully occupied, but you want still want to use relatively little GPU if possible. So we came up with something slightly smarter, where we took all the objects, put them in a priority queue, assigned a weight to them depending on how many instances they have, with an estimate what the BVH costs in memory and things like that. But still extremely simple, priority queue based. Priority queue, pull out the biggest object, put it on the GPU that has the most free memory, and that's it. So extremely simple partitioning compared to your standard object, to your standard data parallel renderer from the past. Let's talk a little bit, about some details. For example, one question is, how do we do the cycling? So how do we communicate the array queues from one GPU to another? There are several alternatives, 2 that turned out to be fast enough. One that we call the implicit method, one that we call the explicit method. And the implicit method is really just where we use CUDA managed memory and build one large global address space over all GPUs. Then we use CUDA's memory advice feature to tell each GPU and to tell CUDA where the array queues are, so that we basically pin array queue 0 to GPU 0, array queue 1 to GPU 1, and so on. And then when we run our array generation shader, every thread knows exactly where to access the array queue after each cycle. So basically like a global address space. And the alternative to this is explicit CUDA memory copies. We tested both of this. It turns out on PCI Express, where you're actually bandwidth limited, much more than on, for example, NVLink. The explicit copies did a little bit better, so we made this our default, also optimizing implicitly for PCI Express a little bit. So that much about how we cycle those rate queues. Another question that is important is how we actually perform shading. As I already said, like we have our trace and cycle phases, and when a trace and cycle phase is finished, the GPU that generated the data also has to perform shading. So this is possible because the hit records are stored with the arrays. Like each array has a hit record. But the problem is that a hit record usually, what does a hit record contain? Like primitive IDs, geometry IDs, instance IDs. That is, with the information of the hit record, you have to do like an indirection to another GPU to retrieve the shading information. So we do something else. What we instead do is, I call them fat hit records. I'm not sure if Ingo is good with that. So we basically store all the BRDF coefficients with the hit record, and if information about the differential geometry that we hit, like the surface normal at the position that we hit, the position in space that we hit, and so on. And that means that when the arrays and their hit records return to the GPU that performs shading, all the information is available that is required to perform the shading. We use the principled BRDF, so actually I have a bunch of BRDF coefficients. We pack them a little bit by using half floats. I think we pack vectors where possible. Yeah, but it's actually, it turned out not so bad. There are several alternatives to implement this, but this is what we resorted to. So another question is scalability. When we're in a system, we have say 4 GPUs available, and we have a model that only occupies 2 GPUs. The question is how to scale. Yeah, we want to use those 4 GPUs, and ideally we also want to become faster, obviously, right? So as I already said, we're doing ray tracing. So we're asymptotically bound logarithmically. That means doubling the geometry doesn't make us twice as slow, but that also means adding more GPU doesn't make us proportionally faster. So just taking the data and instead of chopping it into 2 pieces, chopping it into 4, we don't expect that much acceleration, and we don't expect this to scale so well. So what we do instead is we call this island parallelism. When we have 4 GPUs available and the data fits on 2 GPUs, we just replicate the data and put the duplicate, we put the copy on the 2 available GPUs. Still, each GPU creates a quarter of all the rays. When we then cycle, each GPU still performs the cycle with its ray workload with 1/4 of the rays, but we only have to cycle 2 times because the data is replicated. So yeah, this turns out to scale real well. I'll also show this in the results in a little bit. And it scales much better than the naive way of splitting the data into smaller pieces. And yeah, this obviously, of course, extends to different numbers of GPUs and to different what we call island sizes. Yeah, like if the data fits onto 1 GPU, 2 GPUs, 3 GPUs, and so on. Yeah, talking results. Let's have a quick look at what we evaluated. And the first thing I want to say is, we also did an evaluation on the big irons, like the DGX and RTX servers and whatnot. But one important takeaway here is, if you don't have that, and if you don't need that, your renderer is but a simple wavefront path tracer. Yeah. So I think like the implicit method from before, then your shaders will just access in a global address space, but will access addresses that are on the GPU that we're on. Or CUDA mem copies will not happen if there is no other GPU to copy to. So all this vanishes in thin air, and your whole system becomes an ordinary wavefront path tracer. Yeah? This is actually how we use this a lot of the times. So I mean, for this evaluation, we're really interested in like the big models and the big hardware. So we performed our evaluation on a DGX2 station, which is a Volta architecture-based workstation, which is 16 GPUs, 32 gigabyte each, which has NVLink. That is you have like peer-to-peer communication is on the order of 270 gigabytes bandwidth, which is a lot. But we don't have hardware-accelerated trace because this is not an RTX GPU. And then we use an RTX server with 8 RTX GPUs, with hardware ray tracing. But as an interconnect, only has PCI Express 4.0, which is like roughly an order of magnitude lower on bandwidth. For our test datasets, we used like these datasets that you probably know, like the PBRT landscape scene. I think in 3 different sizes actually. So this slide is missing these. We used 2 different versions of the Moana Island, one smaller, one bigger, where we like replicated some of the textures differently, unrolled some of the subdivision surfaces and so on. And then we also have like a large indoor scene that is bigger than 100 gigabytes in size. And then we performed several tests, but particularly we also performed a scalability test because we're interested in the scalability of our system, where we implemented a simple path tracer on top of our framework, nothing fancy, uses a bit of next event estimation, I think reservoir sampling for some area lights, environment lighting. diffuse BRDFs mostly, and some specular BRDFs for water surfaces, like think the Moana Island or the landscape where there's like water in there. And then we evaluated this, and these are our results for this. On the left side is the RTX server, and the right side is the DGX server. And there's several takeaways here. The first thing to note is that whenever there is a dot in one of those graphs, that means we create another island. Like those two, it's probably not possible for me to, but those two blue polylines up there are models that fit within one GPU. Like whenever there is a dot, we make the decision, use another GPU, create another island, duplicate the data, duplicate the data. And the green line, the dark green line, for example, is a model that fits onto 2 GPUs. So we see extremely well scalability here in terms of this kind of parallelism. And there's also other things that we can see. We can, for example, see that on the RTX server, we are generally faster because we are bound by trace. We can also see that the polylines, when the data gets distributed on the RTX server, which is PCI Express, are all below the 1 GPU lines. That means here bandwidth matters. We can see how the polylines for the models that are distributed among multiple GPUs move closer to the polylines for the 1 GPU model on the DGX, which also makes sense because we have a whole lot more bandwidth. And here we are more bound by trace. Here there's a lot of things to read from these graphs. For comparison, these here are the graphs for the method without islands. Scalability with the naive method from before, where you take the data, and if you have 4 GPUs, make 4 smaller pieces. And you can see that for most of the data, we see diminishing returns, if not even negative. Yeah, that already brings me to the conclusion of my talk. I presented what we think is a extremely simple method. We just distributed the data just as it comes, and then we trace a whole bunch of arrays and wait for them to finish, and then repeat this over and over. So it's extremely simple. And the amazing thing, it's fast. Like I couldn't go into the details here in this talk, but we also beat several of our competitors in terms of frame rates. But the really amazing thing is really how simple this method is. Yeah, from an engineering point of view, and with the very little processing time that is available, that is necessary, and with the engineering constants that are really low compared to your typical data parallel path tracer with all the bells and whistles and complicated splitters and partitioners and so on. Yeah, this is the end of my talk, and I'm now happy to take questions.
Thank you very much for the nice talk. Any questions? Ooh, all the way in the back. I'm going to try.
This is also multiple hop. We have to cycle it through.
So the other sort of like non-trivially large data can be texture. And what if the textures don't fit? Like you didn't really talk about how textures would be distributed or how work would be assigned if textures are on different nodes.
Yeah, this is a good question. It kind of like depends. Yeah, this is a very good question. Like if the textures exceed the memory, I think this is supported. I think that we actually support this because then we can just split the data more. Yes, our partitioning scheme, say weight estimate for the object. So if there's one large object where the textures exceed the GPU memory, then we have some problems. But if not, if like the overall texture memory gets exceeded, then we just split the data more. We just split the data more. We have a weight estimate, and based on the weight estimate, we just use more GPUs. I hope this answers the question. I mean,
partly, yeah. I'm just wondering how the work gets assigned. Because it's not just shuttled necessarily to the next GPU.
Yeah, during the work assignment, we take the texture overhead into account. We compute how much texture we use on the respective GPUs, and we take this into account. Yes.
Okay. I'll ask you later.
Any other questions?
Very nice talk, Stefan. So I'm wondering, do you have a graph where you kind of disable where you have PCI config but disable the ray tracing hardware? just to see the impact on this.
Yeah, this would be interesting. So we're on optics, and you cannot. So like there's RTX on, RTX off, and in reality this does not exist. So you cannot just tell it don't like use the software BVH. We had a software BVH, but for other reasons, because we like the reason being that we also tested with striping the BVH and not just the data. So I remember that this in particular was quite slow, but I'm not sure if this if there's like a certain implementation constants that adds to that. So the question is really like how would like a really well-engineered BVH like the one in RTX, but software perform. I don't know this. I can deduce a little bit from the graphs that I showed earlier that on the Volta systems we're really limited by trace. So that's indicative of that this is an issue. Well, but I cannot really tell. But there's no like magic switch in reality where you can say RTX on, RTX off. Unfortunately.
Okay, thank you.
One question over there. All the way on the left. Yes.
Excellent presentation, thanks. How do you handle shaders that require actual intersection without being able to exit the shader? For example, rounded corners, ambient occlusion, and how do you handle different ray types? For example, you spawn those shadow rays. You mentioned it's a wave front approach. It's not like tracing the entire path and then returning to the same entry point. So this is something that confuses me, and I need a little more explanation.
Yeah, this sounds more like a general wavefront ray tracing question, right? So the question is, what happens if you have like a ray tree and not a ray list, right? With shadow rays, there's this trick where you like take the radiance that you computed with the first ray and then carry it along, compute a shadow ray, and then you still have the radiance, trace the shadow ray, and then you decide if there's occlusion or if the radiance carries through to the intersection. And that allows you to build a list of rays, one for visibility, one for shading, one for shadow, and then like you concatenate these. So, and this in reality, this is what we do in our wavefront ray tracer. Yeah, and for path tracing, which is like a depth search, this is perfectly fine. Like the case where the rays really branch out, our framework does not support this. I haven't thought much about this, how to support this. I'm not sure if it's possible. But for a path tracer, where it's either a depth search through the path space, or you can reformulate the problem to a depth search through the path space. I think this is not an issue. At least this is what I'd say.
Okay, thank you, Stefan.
Yes.
Considering the time, save the remaining questions for the coffee break. And let's thank our speaker once more, Stefan. And then the second paper in this session is on efficient rendering of participating media for multiple viewpoints. And if my notes are correct, you are Robert
Stojanovic. Yes.
There you go. The floor is yours.
Yeah, thank you very much for the introduction. Yeah, I will be talking about how to efficiently render participating media effects in multi-viewpoint scenarios. So to start off with, I want to briefly introduce the goal behind our approach and a bit of the background needed to understand it. When we consider applications like VR, local split screen, and even more relevant cloud rendering, we have the situation that multiple viewpoints of the same scene are being rendered on the same hardware. Using traditional rendering methods, what can happen is that a lot of the computations end up being executed multiple times, which is wasteful. We attempt to remove those or avoid those duplicate computations and optimize the rendering specifically for those participating media effects. When we talk about participating media, we generally refer to effects like fog, smoke, or light shafts. These are created when light interacts with airborne particles, and this is also what makes them somewhat difficult to compute. When we have a scene as it would appear in a vacuum, we can assume that the light bouncing off of objects hits the camera in a straight path. But when we introduce something like fog into the scene, what can happen is that the light now hits those new particles in the air, and it scatters into multiple directions, creating complex paths. In real-time rendering, we therefore use some clever tricks to compute those. There are many different methods to render those effects, and older games tended to use approximations, like rendering a fog based on the depth of the objects, or applying post-process shaders to get effects like light shafts. Those techniques are efficient, but they're not physically based and are more limited to simple interactions. Therefore, more modern applications typically use a different method to render these effects. One widely used method, which is also often referred to as volumetric fog, uses a frustum-aligned 3D volume that stores the incoming light and extinction in voxels in front of the camera. So you can see in the picture here, the colored dots basically represent one of each voxel, or the voxel center. Those voxels are updated every frame and are then accumulated using 2D ray marching through the depth slices, which creates a 3D texture that can then be used to sample the scatter light and transmittance in front of the camera. One thing I should mention here is that with these types of approaches, you would typically use shadow mapping to get the shadow term in the scattering computation. In our rendering pipeline, we do not use shadow mapping and instead use ray tracing to get the shadows. This is more costly, and so we try to keep the ray count to a minimum, hence why we need this approach. So how does our approach differ from the traditional setup? In our pipeline, we have 4 stages, 2 of which are adapted from an existing method, specifically Hilaire. First, we update our 2 data structures in 2 separate steps, and then use those to compute the scattering, and followed by the accumulation. To go into a bit more detail, at the heart of our approach lies the data structure which we call the shadow grid. This is shared across all viewers in the scene, and it's fundamentally quite simple as it is a single world space aligned 3D grid, 3D voxel grid, which is spanned across the entire scene. It stores the result of the shadow ray tracing operations inside of the voxels, and this is implemented as a bit mask where every bit corresponds to the binary occlusion value for one light source at that voxel location. We update the grid every frame, but only consider those voxels which are visible by at least one of the viewers, so that we don't unnecessarily introduce more rays. If a voxel is visible, we shoot 1 ray per light source from the center and store the result inside the bit mask. Otherwise, we can just skip that voxel, since we know that it's not needed this frame. One optimization we made here was using an alternating update strategy to further reduce the costs. Every frame, we actually only consider half of the voxels based on the z-axis index and the frame count. So what we do is we check if the frame count is odd, we only update the voxels with an odd z-axis index, and then the same for odd frame counts as well. This is similar to an interlaced update, except of course in 3D. And with this, we can save half the cost without noticeable degradation in quality. In addition to the shadow grid, we also use 1 shadow frustum per viewer. This works similarly to the shadow grid in that it also stores those ray traced shadows, but it's spanned over the camera frustum, and these are not shared. You can imagine them similar to the picture I've shown before, except it only spans the first third, roughly third of the frustum, and has half the resolution in X and Y. The reason we use them, or we need them actually, is that we have to retain the high density of sample points close to the camera so that we can accurately recreate those effects. And after we've updated both our data structures, we can then compute the scattering for every viewer. This is done very similarly to traditional methods, with the difference being that instead of using shadow mapping, we sample from our data structures instead. And we do this by, or for the voxels, for voxels actually, closest to the camera, we use the shadow frustums. And for those which are further away from the camera, we sample from the shadow grid. Here's a simplified top-down visualization to show you how those two data structures interact and which are used for sampling. Also how the voxels end up being chosen for an update. Optionally, we can do a trilinear interpolation here to get even smoother results. We do this by sampling the 8 closest voxels, computing the scattering at their center positions, and then weighing them according to the distance towards the original sample point. This is slightly more costly, but it can help prevent blockiness in certain situations. And finally, we accumulate the frustums. This is mostly unchanged from other methods where we do a 2D ray march from front to back of the frustums across the depth slices. And this is accumulated into 3D texture, which can then be sampled in a defer or forward pass. Now, I talked a bit about the shadow grid, but I never mentioned a specific resolution. And the reason is that it depends a bit on your needs and what effects you actually want to replicate. We don't actually choose the resolution directly, but compute it from the voxel size as well as the scene size. By voxel size, we mean the edge lengths of the voxel in every world space direction. And we do this because it makes comparing scenes of different sizes much easier in terms of quality. Because of course a fixed sized grid or fixed resolution grid will look very different if in a large scene versus in a small scene. Here's a somewhat difficult variant of the Sponza scene with some gears floating in the sky, and they're rendered with 2 different voxel sizes. On the left, the voxel size was set to 12.5 centimeters, and on the right it's set to 25 centimeters. The difference between them, it's quite noticeable, especially on a monitor, and so it's important to take care in how you choose the voxel size. However, this is also quite a challenging scenario, and in other scenes, which you will see in a minute, we can get away with a voxel size of 33 centimeters or even 50 centimeters. To evaluate our approach, we chose to compare it to reference implementation based on, again, Hilaire. And the setup for that is unchanged, except that we, again, use ray tracing to compute the shadow term. We ran a number of different experiments using a range of multiple view counts from 1 up to 16 concurrent viewers at 1080p each. And for each of those, we used a realistic camera movement paths to hopefully get an accurate representation of real-world performance. Because we want to focus on the performance aspect, we chose the shadow grid in such a way that it roughly matches the quality of the reference implementation. Here's a short video from an outdoor bistro scene showing our approach at a voxel size of 33 centimeters compared to the reference. And here, even on a monitor, it's very hard to distinguish the quality between the two. And the only real noticeable difference is in certain parts. For example, here near the tree, you might be able to see it, because there we have a lot of very fine light shafts. I would suggest looking at the supplemental material for the full-length video as well as some other scenes to see the differences a bit more clearly. Now, when it comes to performance, this is where we can see a difference. On the left, we plotted our approach with running in 2 different voxel sizes against the reference implementation, and found that as more viewers are present in the scene, the better performance we can see. This is not really surprising, however, because at some point the shadow grid will become saturated with updates, and so the performance cost for that starts to taper off. On the right, we see an artificial setup that fixes the overlap between the cameras, so that we get a sense of the range of scaling we can even achieve. Unsurprisingly, as more scale or as more overlap is present, better our approach scales. But even with a small overlap of roughly 10%, we can still see a performance uplift with 8 or more viewers. And when we have a lot of overlap, like in a VR situation, then the performance uplift can happen with just one viewer, one user, or 2 cameras. When it comes to memory consumption, we still use the scattering and accumulation volumes found in the traditional methods. And in addition to those, we use the frustum volumes, the shadow frustum volumes, which are less than half a megabyte per viewer. And we also need the constant amount for the shadow grid. How much, of course, depends on the chosen voxel size as well as the scene size. But to give you an idea, in the bistro scene you saw earlier, this amounted to roughly 100 megabytes at the voxel size of 33 centimeters. One challenge we found during testing was that choosing a voxel size that both preserves the details without costing too much is not that trivial. Ideally, we want to have a high resolution in areas where we know this is needed, such as near trees, because those produce a lot of light shafts, and less in other areas. We ran some initial experiments using multiple shadow grids with varying voxel sizes. And besides the increase in memory consumption, the results appeared quite promising. Alternatively, we might also be able to use an octree-like approach to have a more optimized distribution of voxels. One thing that we did not deal with our approach was clouds. Because clouds are usually quite far away from the scene, it didn't make a lot of sense to extend the shadow grid to include them. And so you need an alternative method like ray marching to compute them. But this is also what is usually done in volumetric fog methods. In the future, we might be able to use a unified approach that also shares the computations for rendering cloud effects. And if you're patient, there will be a talk later on that talks specifically about that. So to conclude, we developed an approach that is able to render participating media effects at up to 60% faster with 16 viewers. We are able to see a performance uplift with as soon as 2 viewers, and we do this while maintaining a quality level close to that of competing approaches. I am done, but I see that I still have a bit of time, so I maybe want to show you a few more results. So here's the flip result of the Sponza scene you saw earlier, and you can tell that the 25 centimeter voxel size is quite a bit, yeah, it's not really ideal, but the 12.5 centimeter one is actually quite good. And here's another image of the bistro scene, this time with a non-uniform fog volume with 2 different voxel sizes again. And here's the flip result. So here we can see that even with 50 centimeter voxel size, the difference is still quite acceptable. So yeah, that was all. Thank you. Oh, sorry.
with a big explosion at the end. Good. Thank you very much for the presentation. Any questions from the audience? Yeah? Long flight?
Sorry, in case the view are closed, like in the VR approach, have you tried with a clip map? So like a concentric grid with the like bigger size as far as you go from the view?
We did not try that, but that is an interesting idea, yes. So maybe in the future.
Okay, thank you. Thanks for the presentation.
Thanks.
Hello? Does this work? Okay.
Yes.
Nice presentation. Have you maybe thought about to do a little bit of work on the client, so to say, for example, right at the edges of your, let's say, coarse voxel grid? You could maybe take a couple of samples when you know that you're at the edge, and then do on the client, like to smooth out the shadow.
Can you repeat it? I didn't quite understand.
Okay, at the very edge of your, like when you're on the client and rendering, and you notice that you're at the edge of a shadow, like then you could maybe choose some rays as the client to like smooth it out and have a high res simulate a higher res grid.
So there's actually what's usually done with those other volumetric fog approaches, and we do as well. You can do a trilinear interpolation again after or during the sampling in the deferred or forward pass, and this also helps, but it can result in a bit of like temporal issues because it will get very smooth and very like ghosty. Yeah, but yeah, thanks.
Anyone else? Okay, I have one question. Would it also be possible to have other volumetric effects like light emitting from the volume with this approach?
Maybe, but it will cost a lot more memory likely. So now we only use 8 light sources which fit in 1 byte, and this is really efficient. You can of course extend it to add more lights as you need them, but at some point, especially in large scenes, it will become quite expensive to store that. Yeah.
Okay, thank you.
Thanks.
All right, let's thank the speaker once more. And then the next presentation is also addressing the issue of rendering in the cloud for multiple views. And the next paper is surface light cones sharing direction illumination for efficient multi-viewer rendering. And that is going to exploit the fact that incoming radiance for surface points is view independent, unlike the reflection, of course. And it uses this notion to cache radiance information on the surface of the scene. And this will be presented by Pascal Stadbauer. Floor is yours.
Thank you for the introduction. Welcome to my talk about surface light cones sharing direct illumination for efficient multi-viewer rendering. So typically cloud rendering systems render images on an instance basis, and they do not usually share any computations between the instances, and this causes sometimes redundant computations. So if you, for example, think of team-based games or presentations or VR setups where cameras are all in the same location and looking at similar stuff, then this, of course, leads to the idea of information sharing. So the question in our research is, can we share the shading? To determine that, we look at the rendering equation, which is the basis for most realistic shading, and ask the question, what can be reused? So on the left is the emission of the surface, which is of course view dependent, but fast to evaluate, so we don't pay much attention to that. And the more computational expensive part is of course the gradient, the integral, because it integrates over the whole hemisphere. And in there is the BRDF, which is of course view dependent, which is multiplied by the illumination and the cosine. So the thing here we want to reuse is of course the illumination, and when we look at it into more detail, then we can split up the illumination into a direct part and an indirect part. For the indirect illumination, many approaches exist. Due to the low directional variance in this kind of data, you can use spherical harmonics or this kind of stuff. But for direct illumination, the data is very highly directional dependent, so it's not easy to express. And our question is if we can find a representation to express this kind of data. So for this, we propose to use surface light counts, which represent all incoming radiance on a certain surface point from all light sources, as you, for example, see here in the picture, where the radiance is represented, the radiance from the street light is represented by those 3 cones. So in our representation, we have a multiple of cones. In practice, we use 3. And then we have the cone count to know how many cones are active, and an accumulation count to accumulate the radiance efficiently. Each cone consists of a direction, an opening angle, and the radiance it gathers. So now that we have defined this, this representation, the question is how do we implement it, and how do we, for example, allocate the surface points, this kind of stuff. So for this, we use an implementation that's based on the paper Effect-Based Multi-Viewer Caching for Cloud Native Rendering by Wijndorf and Ozkan et al., which will be presented at this year's SIGGRAPH. They use a combination of world space caches and on-surface caches to reduce computations and share data between users for various different effects. So we use the on-surface caches, so a quick overview about that. So the first visibility buffers are fed into the system. The visibility buffers of each user is fed into the system, and the visibility stage determines which cache entries are active. Then some scheduling and processing is done, and then the cache update stage updates the cache entries on a effect basis. So for example, AO and hard shadows here. And after that, the composition stage creates the final image by sampling the caches and compositing the image. So what we add is the surface light cone update to the cache update stage, where we retrieve the cones if they are already represented. Otherwise, one can, for example, fetch them from a different LOD or such. And then we integrate the new data into the cones and update the cones, and then we store them again. With retrieving and storing, I mean the base system. So the cones are stored in a texture format because that's given by the base system, and so we have to do some bit magic and format conversion to fit it in. And after that, on a per viewer basis, we add the shading, where we retrieve the cones and then sample the cones and create the shading and composite it to the other colors of the other effects. So for the update process, I have a very simple scene here. For each surface cache entry, we random sample all scene light sources, so emissive surfaces, environment maps, and area light sources. So just an example here, we sample the scene light source, and if it's not occluded, we add a cone, and we continue like that. For occluded scene light sources, of course, we dismiss the samples. And for samples that are not occluded and close to another cone, we merge it to the new cone, to an existing cone, and we continue like that until we have our representation. So this is, of course, now only for static scenarios. What if for example, this wall fade disappears now. The operations before can also handle this by just sampling the new light source at the new unoccluded light source at some point and adding to this cone. But if this wall appears again, the operations before wouldn't suffice to adapt our representation to fit the lighting situation. Therefore, we also sample the cones at the borders, some epsilon away from the borders, and if this sample doesn't hit a light source, then we shrink the cones. We continue this a few times until we have the right representation again. Of course, usually dynamic changes happen slowly, and so we don't need that many samples to adapt the cones. Yeah, in practice this looks like that, where the light source moves from left to right, and in the center image you see that the surface point becomes partially occluded, and this is where the cones split up into two. And after the light source continues moving, the cones merge again. And yeah. So I mentioned temporal accumulation quickly before. So we do this very simple, where we have the old value times factor plus the newly sampled value times the factor, and that's how we get our new radiance. But for and this factor is based on the accumulation count. So the question is if we just can simply increase the accumulation count, and this is not the case when dynamic changes happen, because newly added radiance wouldn't be that wouldn't be that quickly integrated into our representation, and that's a problem. Therefore, when a change happens in the scene, we reduce the accumulation count a bit by this formula, which worked well in practice. And by reducing that, the newly changes are applied in a more quick manner. Yeah, this accumulation count is adapted based on the angle of change of the cone, and yeah, in practice that worked well. So for the shading process, now that we have our cone representation, we can just simply sample a cone and then evaluate the BRDF for this cone, multiply it by the radiance of this cone divided by the number of samples, and multiply with the cosine. And if we do this for all cones, then you kind of represent the integral of the shading equation. And if you continue to add the emission, then you have an approximation of the shading equation again. Of course, this is more accurate the more cones you add, because you better represent incoming data. So for the evaluation, I want to first quickly show you the single viewer data and to establish effectiveness there, and then continue with the multi-viewer. Yeah, for evaluation we have chosen 3 cones because overall this worked well in practice. And yeah, you see Viking Village here as one of the test scenes, which we compared with the simple reduced version with 16 samples and 48 samples. 60 samples because it overall compared very well to our timings, and 48 samples because it compared overall good to our quality overall test scenes, of course. You can see here that we outperform other measurements, other approaches, like for example at RTXDI. And yeah, let's look at some other scenes. Here you see San Miguel with an environment map and the lamps activated. And here's a version of Intel sponsor scene, which we adapted a bit and placed different lights. We also have a bistro exterior scene with moving lights and moving gears to show dynamic changes. Here you see that we are a bit slower than RTXDI because we have to adapt to these faster dynamic changes. And there is the Viking Village from before, where a large moon is placed and the torches are activated. So now that we establish effectiveness for the single viewer case, let's go to the multi-viewer. Here's an example of the sponsor scene you just seen before, with a camera overlap of 60%. And overall, if we don't start out with better performance for one viewer, after adding some viewers, we achieve a better performance at some point, as you see here. Yeah, let's look at, so different overlaps result in different timings, of course. So this is as you would expect. For overlap of 100, you have this, just a overlap of 100, you have this minimal overhead, which increases the timings a bit here. And this is also for the sponsor scene. So let's look at more natural example. We have 16 uncorrelated paths through the sponsor scene, which look like that. Yeah, so they move uncorrelated through the scene. First, they look all in the same direction, and then they move uncorrelated. Of course, this is shown for our approach for 16 single views and now 16 stereo views. And this leads to the following results. So on the left, you can see the 16 single viewer version, where we outperform the other methods. If we have 8 stereo views, so still 16 views, but with a higher overlap because they're in a stereo position, then our timings go a bit down, while the others approximately stay the same. When moving from 16 single viewers to 16 stereo viewers, we see that all other methods double the timings, while ours doesn't. For RTXDR, we couldn't run an experiment here because it ran out of memory for this amount of views. So talking about memory, here you see a memory graph for the sponsor scene, where you can see that the ray traced version doesn't use additional memory because it doesn't keep track of anything between frames. And you see that ours increases steadily, while RTXDI always doubles in memory because it always needs to keep track of the screen space parameters and and of the reservoirs. So what are our limitations? So of course, these 3-cone representation has a limit at some point. On the left, you see the scene with a lower number of lights, on the right with a higher number of lights, and you can see that when we increase the number of lights, that in certain areas where there are too many dominant lights, the cones try to include a too large direction, which leads to noise, as you can see in the zoom in here. Of course, a solution to this would be to just increase the number of cones. Yes. So we also handle environment maps, but this of course is an edge case again, where the lights all spread out over the hemisphere, which causes again the cones to be too large, and then this causes noise again. Yeah, this also happens if you have too many small lights that all spread out, and yeah. Of course, you can increase the number of cones again to express this, but yeah. So to conclude, we've shown a cone representation for incoming radiance and integrated this into a pipeline and showed how that the reuse is efficient. Therefore, we outperform other methods for the multi-viewer case and also sometimes mostly for the single viewer case. As shown before, this expression isn't always enough to express all light scenarios. For example, you have these surrounding lights, then for example, spherical harmonics would be better, or you have these multiple small lights where you can, for example, use visibility caching, and this would be faster. So simple shadow mapping and this kind of stuff, which would be faster. A complete system would, of course, include those other methods and switch between them, and that's something for the future work. Thank you.
Thank you very much. Nice presentation. Any questions from the audience?
Thank you for the talk. I was wondering, when you explain how, if an occluder appears, how you shrink back the cone. What happens if the occluder appears in the middle? For example, if you only had like one straight line to start with, and then the line maybe starts rotating and occludes more and more of the cone.
So you mean in the, sorry, I didn't get it fully.
So if you have like a large cone like this, and then you have an occluder that was maybe like a thin line in the middle, but that starts rotating and blocking more and more of the cone. With your approach, or how do you describe it? It seems like you would trace samples on the sides, but those would still not be occluded to start with.
Yeah, noise will probably appear in that case.
Okay.
And yeah, the radiance is still right, but you get some noise if in that case. Yeah.
Okay, thank you.
Anything else? Then I have one question. I saw some very nice comparisons against RTX DI. I can imagine that when you increase the number of light sources, this comparison becomes less favorable at some point. At which number of light sources is that going to be, roughly?
That's very dependent on the scene setup and the light setup and how dominant the lights are. So it's difficult to say. If you have really dominant light sources that are really shining on a specific point, and then it's probably larger than the number of cones, but if they're not the dominant, then yeah, they would last longer. So
the technique strongly relies on having some very clear dominant light sources.
Yeah.
Yes. Okay. Thank you. Okay, thank you, Pascal. Oh, there's one more question over there, and I think we still have time for that.
Thank you. There was a grid-based variant of FreeSteer for direct illumination where the reservoirs exist in a clip map. So I imagine that would also enable some reuse for different views. Have you considered that or compared to that?
No, but I need to. I will consider it now.
Okay, thanks.
Okay, thank you, Pascal.
Thank you.
And that takes us to the final paper for this session, which is also using caches, but this time to take cloud rendering to the next level, because we can of course render in the cloud, but we can also render clouds in the cloud. Clouds in the cloud, efficient cloud-based rendering of real-time volumetric clouds, and the presenter is Alexander Wijnrauch, who is going to show us if the sky really is the limit.
Yeah. Thank you for a nice introduction. And welcome to my talk about clouds in the cloud, an efficient cloud-based rendering of real-time volumetric clouds. So it's like a buzzword bingo, and there will be a lot of more clouds in the slides. This work was a joint effort by Carsten University of Technology and also Huawei Technologies in Austria. So why do we care about clouds? Probably all of you know this beloved wallpaper back from the good times. And the clouds are here very important. Just imagine if you would exchange the cloudscape here, this partly clouded clouds, with a clear cloudscape or a thunderstorm. This would completely change the atmosphere of the picture, pun intended. So from this, it's natural that we have a lot of ongoing research in this topic. This dates back probably around 40 years or something, so older than I am. The simplest approach is probably skyboxes, where you have just pre-rendered images. Probably all are familiar with those, come in different flavors, like cube map texture or spherical mapped images. Then we have more dynamic approaches with like billboards and imposters, lookup tables, metaballs, Recently, there was a surge, especially in AAA production, real-time games, ray marching-based approaches, and also recently there are some neural networks which still not work in real time. Probably as AI evolves, will probably become real-time possible in the near future. In our work, and also in this talk, we mostly care about ray march-based approaches. Just a really quick overview, because it's not that important for the talk and also for the paper, because in theory, our caches work with other techniques as well. But in ray marching, you just, for all screen pixels which are not occluded, you just ray march from a lower bound where your clouds can form towards your exit where the clouds stop to be appearing. And in your ray marching steps, you just calculate density. This is usually done by looking up a weather map where the artist has control where clouds can form and their properties, as well as some 3D noise textures, usually a combination between Perlin and Wally noise, to give the clouds its shape and their random details and fine and coarse details. If you're interested in more details, I highly recommend, if the slide changes, the talks by Andrew Schneider from Gorilla. They were part of the advances in real-time rendering for games at SIGGRAPH 2017 and 2022, I think. So there he goes into much more detail how the system can be implemented. So now that we know why we use clouds, why we need clouds, and also if you think about, so I haven't discussed this here, during the sampling you also need to ray march towards the sun to get like in-scattering effects. So you have a lot of work to be done here because those multiply with your first step sizes. So ray march-based approaches are quite expensive. So I just recall one number on old generation hardware, so PS4, even at quarter resolution, it still took about 2 milliseconds for the Horizon game from the talk by Andrew Schneider. So this is quite computationally expensive, even on today's hardware. So what can we do? We can move it to the cloud. And the first thing would probably be, yeah, we have the more powerful hardware. But actually, we aim at sharing computations between viewers, so get down the overall cost in computations. And for this, just imagine a really simple VR application, for example, like I think there is something like this, like a fighting game in a Colosseum, where players just randomly, or totally randomly run through the scene, and then you just visualize on the right, if you would have a skybox, how often is a pixel of the skybox actually used. And there you can see here in purple that for many viewpoints, a large portion of the screen can be reused, so we can share their computations. So there is a high potential for saving on hardware budget or energy, or both. Now comes the question, cloud computations, when you go beyond a simple skybox, are view dependent. How can we actually share those computations between different viewpoints? And for this, we need to cache them somehow. And we had some simple requirements. The first one was to have a really easy integration path into existing rendering techniques and pipelines and game engines. We want to have the same visual quality, a really low overhead, and support for different cloud rendering techniques. And for this, there was a paper before in Pascal's talk. We use our work effect-based multi-viewer caching for cloud native rendering. And also I and Wolfgang will present this work at SIGGRAPH in around 5 weeks, I think. So we use the on-surface caches to store the clouds on. A really quick overview. They are object-based caches, where you simply have multiple resolutions. They're completely software virtualized, so you only require memory where you store information on. And it's about resolutions from 1 by 1 up to 64 by 64K, so you can really get close to the clouds and far away from your clouds, and the system covers you all. However, now comes the elephant in the room. Where do we put on-surface caches on for clouds? Because usually clouds don't have geometry. Especially for the ray marching approaches, you don't have any geometry at all. And what we can do here is the most simple approach is just place a sphere around the scene. Simply, very similar to Skybox. What you do is in the first step, you determine which pixels of your sphere are visible by the viewer. This is handled by the on-surface caches. Then you have a separate update stage where you have all the pixels which are required in a work queue. From this work queue, you compute back your origin. In this case, you can just use the center of the sphere or the camera if you have a simple one single camera, and then do your ray marching into the clouds and store density and color information, which is usually enough to reproduce the final shading. However, now when we add multiple viewers, we have there one problem. If we use the computations from before, here shown in green, and you move the camera in the sphere, you will actually have a misalignment between your view rays in red, the second camera, and your cache update location, because cloud computations are view dependent overall. Now comes the question, is this an issue? And when you render it, it looks quite awful, especially if you move far away from the center. And you can see, I hope it's visible, distortions of the clouds. You can see that those are not really 3D anymore. So yeah, we will see later how far we can push the system in this direction. However, there's a bigger issue with, hopefully if the video works, probably a bit not good quality, but still the clouds look like billboards if you use this simple setup. So this is not really working great. Okay, so what we can do here to improve and add this parallax, which is present in nature because clouds are at different distances to the viewer. They move at different speeds when you move through the scene. And to reproduce this, we can add multiple spheres. And here's a simple example with 2 spheres. They cover just some intervals in your atmosphere, and different clouds are stored on different spheres depending on their distance to the viewer, or the center of the sphere in this example. There's just one small issue. If you have a cloud spanning over multiple spheres, you have to be careful to store it on a single sphere, because otherwise you will have a problem that when you move, the cloud will slice into 2, and you can see the inside of the cloud, which usually has not a great shading information there. So what we can do is just extend the ray marching outside of the cloud and then switch to the next layer. And then we have the cloud on a single layer, which then solves this issue. However, there's still one small problem with this approach, is when because your planet is obviously, or most of the time, larger than your scene. So the bounding box of your scene, where you scale your spheres off, are too small to cover the whole planet. And then clouds which are far away are still on a single sphere. So you have the same problem when you look close to the horizon. And to fix this, we can just scale everything up. So now we take the planet scale into account. So our caching spheres here in blue and orange now have a constant altitude around the planet. Obviously now you have a really big sphere. So we have in the paper a small section about how we create this, because usually if you know how high you can go in your scene, you know how much of the sphere you actually need, because the other thing is blocked by the surface of the planet. And also we can get away with some adaptive resolutions, because close to the horizon, usually due to atmospheric scattering, you cannot see small issues there. So you only need a good resolution at the zenith of above your update point. And also, speaking of the update point, we also move it from the center of the sphere to the surface of your planet, because otherwise you would have distortions even at the center of your scene. So, and this then fixes the issue, because the clouds usually follow the surface of the planet in terms of altitude, our caching spheres as well, so you can then don't have problems there. And this also now has like a parallax effect, so you can here, for example, see the things with our method. So the update position is fixed, so this is wrong. So the clouds look different because they move a bit different still. However, it looks much better than the single sphere approach from before. Okay. And before I talk about the server structure, quickly note here, we also do cloud shadows. They are a bit of a free lunch, so this is not a small section in the paper, also in the presentation, because on-surface caches work on the surface already. They are view independent, because they only are like a dampening factor of incoming light. So we can just simply add to the on-surface caches a simple compute shader, ray marching towards the sun, accumulating the density values, store them in the caches, doing the rendering, just dampening the incoming light based on the density of the ray marching. This is really simple and yeah, nothing really new here. But this allows us to share it between multiple viewers. Now comes the question, how can we distribute the viewers to GPUs? And for this, because I said already before, when you move far away from the center, you get distortions and get a generally worse visual quality. So what we propose are like view cells. View cells group many viewers. They have the same set of caches, so they need to be in the general vicinity. For example, if you have a game, you probably know some hotspots where people will gather, like town halls, auction halls, some global events or anything. And there you can just place static view cells with a fixed size. And also if you have, for example, a cooperative shooter game, like a famous zombie shooter, you know probably that the users move as a bulk a view your scene. And you can also have like a dynamic view cells which moves through the scene. And in the paper we also have a user study about how much your movement can differ from the movement of the average view cell, so you still don't notice the wrong renderings, which is not covered in this talk, but there's a bit about this in the paper. And for actual server configuration, so what we do is we split view cells to GPU nodes. We only had a GPU node with 8 GPUs, Tesla 8, I think 1000 or 9000, not sure. The one which is similar in performance to 3090. And we split them into output GPUs. So what they are doing is they render the visibility buffer. So this is required for down-surface caches. Really simple, just render your unique triangle ID of the scene. This is then sent to the effect GPUs. I will cover them later. After this, or while the transfer is happening, the GPU can render everything not cache related, so the whole scene without clouds and cloud shadows, then waits for the data from the effect GPUs. And what they get are all the V-buffers, does the deduplication on surface cache related, then does the cache updates, which is the ray marching I talked before, and then renders the images with only the clouds or the cloud shadows. And this is then sent back to the output GPUs to the correct one, which then combines both images, does some post-processing like tone mapping, and then there's also the encoding in a video stream. And from this then we don't really cover in the paper anymore, because from there on we don't have any novelty there. We just send the data to the client, which renders the image and sends the input, so there is nothing new there. So how does the system actually fare in terms of visual quality and scaling? For visual quality, the left one you can see like a reference implementation. Looks a bit bloggy on the beamer, sorry for that. On the right side, you can see our cached rendering. So this is without compression. This is just comparing the system, your potential visual quality when you don't factor compression into account. You can see not really differences. Also, when we visualize the flip error metrics, this is not the beamer. The image is actually close to black at every pixel, because there are only some tiny errors, because the object space caches do not always align perfectly with your screen space pixels. So you have there a sub-pixel misalignment, so the ray marching direction will be slightly different. However, you will not really notice a visual difference by this. And actually, on-surface caches can also lower the resolution in the form of a mid bias. And there you can see, as you increase your mid bias, you will see that the errors actually will increase, because the caches just cannot represent the high frequency of the information of the clouds. And for this, we also did a user study where we had 16 participants. They're watching movie clips for a reference, different mid biases. And from this, just a short explanation is, you can see that up to mid bias of 2, you probably will not have a problem with your viewers. However, when you go beyond this, there will be a sharp decrease in visual quality. Obviously, this depends a bit on your scene. So if you have more details in your clouds, you'll probably will shift the scale towards mid bias of 1. So this is just a baseline when you're implementing such a system. The next question is, how far can we actually move away from the center? So in this VR example from before, there were like 9 meters, because the center was the middle of the arena. There we cannot really tell a difference. And we scale it up to 90 meters. Now the clouds look different, especially if you look at the holes in the carousel. There you can see that the cloud moved differently. To be expected, because we still cache them on a specific distance to the viewer, but in the real the reference implementations, they have varying distances in the range where the sphere is placed. And if we scale it up to 3,200 meters, then you can again see the large distortions towards the center, and then the user will probably tell you this does not look great. And this is also what our user study suggests. So what you can see here is when you move upwards, you can get away only with probably around 1,000 meters. And in the horizontal plane, basically double that amount is to be expected. When you move upwards, you reduce the distance to the clouds much more quickly than moving in the horizontal plane. So we'll see the errors much more quickly. And now to the runtime. So what we did is we rendered the clouds without a scene. So there's like the the worst case in terms of memory consumption and in runtime, and have like a fixed overlap experiment where they move on a random camera path just to simulate some movement. So you get like memory allocations from the surface caches to make this a fair comparison. And what you can see here is with no overlap. So the overlap is controlled by putting them on the same position, but rotating them around the up axis. So then you can control just the overlap of your field of view, which nearly directly correlates to the overlap in the surface caches, so the shared computations. And here you can see with no overlap, this is the light blue line here, we are slightly above the reference implementation, which just scales linearly with the number of viewers, because we don't share any computations there due to cache overhead. And as you increase the overlap, you will see that our runtimes linearly decrease, as you would expect. And when you add a mid-pass to it, you basically just halve the amount of time we take to compute our shaders, our caches, and from passive 2, this scales nicely, as you would expect. There is some constant overhead to it, as I said, due to cache management and cache allocation. In terms of memory, so you can see the memory for 16 viewers. So in a worst case scenario with unbiased caches, we use with the additional buffers like 1.3 gigabytes, which is usually not a problem, even on consumer GPUs, as long as those are not modern 1080p cards, then 1 gigabyte shouldn't be a problem. And as you increase the mid-buyers, the memory again will halve basically, and will linearly decrease with the number of the overlap percentage you achieve in your application. And with this, I want to conclude my talk. So what we show in our work is how to efficiently share view-dependent data in a view-independent manner. We show that it scales with the overlap and has the same visual quality when you don't apply a mid-bias. And even with some form of mid-bias, you can still still achieve quite similar perceived quality. And also in the paper, we have like system baselines if you want to implement as a system, which can be a good guideline when starting implementing this. And with this, thank you for your attention. I'm looking forward for your questions.
Thank you, Alexander. Any questions? There's one question here on the front row.
Thank you, very nice talk. So I'm curious what your motivation is to use ray marching. Because I have a hunch if you would instead use free flight distances, that would in certain cases make things easier. For example, you said there's no surface hit. Well, the free flight distances would give you one.
I'm not familiar with free flat surfaces, but in theory you can just exchange the method. So it's not really important that we use the ray marching, because what you get in your update shader is your surface location where the cache is placed, your center, that's everything you have. So all methods which can calculate the pixel value with those two pieces of information can be used in our system. So it's not really ray marching specific at all.
But your depth, so to say, is flat, right? Like it's on the sphere surface.
The depth of the sphere, or I mean, it's closely to flat if you are on the ground level, because the atmosphere is mostly flat. If you mean this.
Yeah, thank you.
Yeah, sure. Okay. Anyone else? We have time for one more question.
Okay, I will ask you. What kind of sampling along the ray for the ray marching you use? Is this like regular sampling, or
no? So
with some Woodcock sampling, or which one?
For the ray marching, this is basically just an adaptive step size, if you mean this. So when you are inside a cloud, you lower your step size, also go a bit backwards, so you find the beginning of your cloud. This is the same as what was described by the talks of Andrew Schneider. So you go back half the way. See if you're still inside the cloud, go again back halfwards. When you found the start of your cloud, you have 1/10 of your step size approximately. When you're outside, you can increase your step size, and that's the sampling you do in the ray marching.
Yeah, but I mean, you can use more efficient sampling methods.
Probably you can, yeah. But then, of course, your screen space will be faster, so this should stay closely the same. Because what we do, the overlap basically defines, so we do the same thing. So the good thing with surface caches is that you can just share your update shader. So between the screen space implementation and the cached implementation, there are like 3 lines of code different. It's just how you get the information about the position and the direction. So you can just plug and play with whatever you want, and they should give you the nice scaling, because the cache overhead, it's quite low. So you can see it from this one. Even if you have 16 viewers, so you can see it, it went up from 60 to probably 64, and this is still quite low. And for clouds, you can even optimize a bit more to like half this number.
Okay, thank you.
Okay, all good. Then thank you, Alexander, once more. And before we leave for a coffee break, Matthijs wants to have a word with you.
Hello, so I know I'm stopping you all from the break. So we have a poster session downstairs, and we have 2 excellent posters. I'm encouraging everyone to take a look. So one is about the bright future where all GPUs get replaced by machine learning accelerators and you still want to ray trace. So that's on the right pillar if you go downstairs and look at the wall. And the other one is if you're getting like real world triangle soups and you actually want quad meshes. So there's another excellent paper on the left-hand side where this is finally solved. And with that, I encourage everyone to take the time and spend half an hour on each poster, please. Thanks.
Test, test, test. Hello.
Okay. Welcome back, everybody. I am Christoph Peters, and it is my pleasure to introduce our second keynote speaker, Chih-Chen. Chi did his Bachelor of Engineering at Tsinghua University in Beijing, China, and then did his PhD at UC Berkeley under the supervision of Ravi Ramamurthy. During his PhD, he worked at Disney, Autodesk, Weta, and also at NVIDIA, where I had the pleasure of being his colleague. His PhD thesis received the Outstanding Doctoral Dissertation Award at SIGGRAPH 2019, and he has made a stellar career and is now an assistant professor of computer science at UC Santa Barbara, a co-director of the Mirage Lab, and affiliated faculty in the 4ICE Lab. His work covers the full breadth of rendering research: offline and real-time, appearance and light transport, wave optics and neural approximations, glints and denoising, hair and scratches. There's something for everyone. He has excellent connections with both academic and industrial research. As far as I can tell, every major tech company is already funding his work, but if yours is not, you should probably change that. So I'm very honored that you accepted our invitation, and I'm looking forward to your presentation.
Thank you.
Please take it away.
Okay. All right. Good afternoon, everyone. Yeah. Yeah. Thank you. Okay. Can you hear me? Yeah. Okay. Great. So yeah. First, thanks, Christoph, for the introduction and the invitation. Okay. I actually can't believe this is my first time attending HPG, but it is my true honor to be here. Okay. So in the beginning, Christoph told me that I can talk about everything, right? So, and I said, great, I have an entire hour to complain about how difficult to get funding for rendering research in universities. Okay, all right, but later I changed my mind. So seriously, my research is about photorealistic rendering, and it seems contradictory to high performance because photorealism often means heavy computation, but let me try to relate them today. I will introduce a few recent works of mine, very quickly skimmed over with high-level ideas. More importantly, I plan to raise more questions and share thoughts with you rather than providing solutions, because honestly, I don't have any solutions to either high performance or photorealistic rendering. Okay. So rendering. What is rendering? To me, rendering is the process that turns 3D geometry into images. With different lighting conditions and appearances of materials, we can expect different images, so rendering is computing. Then what is photorealistic rendering? The word photorealistic is clearly made up. We want the rendered images to be realistic. How realistic? As realistic as real photos, like this picture. I bet it's difficult to judge whether it's rendered until you see the 3D model. As I said, when we are pursuing photorealistic rendering, we often have to impose burden to the performance. Why is that? And is it possible that we achieve them both? To answer these questions, I plan to talk 3 parts today. I will first focus on complex appearance and geometry, respectively, and then I will talk more about ideas and thoughts. Let's start with appearance. I used to say shading. I don't know what you think, but I feel that shading nowadays is more involved with light transport rather than the intrinsic optical properties of different materials, which is my understanding of the definition of the appearance. From this definition, we can immediately say that the appearance is definitely not just these images shown here. Why appearance is difficult? I have summarized 3 most important properties of appearance: high dimensional, high frequency, and high rank. High dimensional is relatively easy to understand. A BRDF is 4D, a neural radiance field or NERF is intrinsically 4D light field, but since it's no longer defined on the surface, but rather in a volume, it becomes 5D. And for example, a BSS-RDF for subsurface scattering is 8D, etc. High dimensional means that it is often difficult to measure, store, and synthesize appearance. And high frequency means that the modern appearance is no longer like diffuse plus specular. It can provide drastically changing pattern over time. And high rank means irregular. For example, we know that the cloth weave pattern is repetitive, but actually, there are no places that are exactly the same. So how do we acquire realistic appearance? Let's recall our high school chemistry and biology courses, because my teacher often say that structure determines function, right? So as I mentioned earlier, since appearance is some optical property or function, to study appearance is to study the underlying structure of certain materials. This study often goes from faraway view or observation all the way down to the microstructure. That's why I name it top-down analysis. To understand how it works, I'll take this work, sponge cake model, as an example. It'll be presented at this year's SIGGRAPH. Why do we want this model? There are different kinds of reflectance models. For example, the foam model that can represent some plastic-looking appearance. And the microfacet model is good at representing conductor and dielectric. We would like to ask, is it possible to find one model that is physically based and does everything, including layering, transmission, sheen, multiple scattering? And our sponge cake can do it. So you can see that the sunlight from outside can go through the two-layered curtain of ours, giving some transmission effects. And when the light only comes from inside the room, for example, in the night, we can see the reflection. And we can also combine them together to get a bright room. So why do we call it sponge cake? Because our model looks like a sponge cake. That's the structure. So we find the common materials share similar layered structures. Each layer has some thickness, and their materials can be different. For example, wood and the varnished layer on top of it. If we ignore the interface between the different layers, it is indeed a sponge cake. So we can derive an appearance model. Given incident and outgoing directions, we can integrate on all possible places along the depth where the light may scatter, and find geometrically how much light is absorbed before, scattered at, and absorbed after the scattering event. So for single scattering, we have a nice analytic model. Later, we have extended this sponge cake work to support surface-based cloth rendering. The cloth is even more complex because of its three-level twisted structure, as you can see from the image on the top right corner. From left to right, fibers twist to form plies, and plies twist to form yarns. And yarns are finally woven or knitted to get a piece of cloth. So traditionally, there's been fiber-based cloth rendering approaches that accurately model and trace individual fibers, and also volume-based methods that turn fibers into scattering properties in a voxel grid. These are relatively accurate methods compared to the surface-based methods, but of course, more costly. So we would like to make the surface-based cloth model better with designed details and a good appearance. And we do this by defining a series of textures on the surface. These textures are tileable and can be either high resolution in the first row or low resolution in the second row. They are able to determine very fine structures of the cloth surface. For example, a cloth is woven or knitted with yarns contacting each other, right? Like in this way. So they cannot produce a watertight surface. So when a ray hits the gap between the yarns, it should go through directly without hitting anything, right? Then it's the structure of the plies twisted together. So basically how the plies will follow the movement of the yarn. We need its per point normal and tangent. And in this way, we do not need to specify any fibers, but we can infer the fiber's direction whenever there is a ray intersection with the ply. Then we can shade as if there are fibers using our sponge cake model. And finally, the surface of the cloth is never flat. Higher places will block rays or eyesights from reaching lower places. So we keep a height field and use a 2D anisotropic Gaussian to approximate the 2D visibility at different places. And in this way, we're able to get a nicely looking cloth on triangle mesh with actual weave patterns, transmission, sheen, and other nice properties. But let's stop for a while. As we can see, the top-down analysis gives us good appearance. But isn't this too complex for fast performance, right? Just like this Linux meme. What we've been doing is equivalent to saying, hey, here's your microstructure. Please go ahead and ray trace yourself. So what should we actually do? So let's take a look at this example. So I had this animal fur project when I was a student. I found that the hair reflectance models are not suitable for animal fur. And I did some research on biology, and I found the structural difference. Unlike human hair, which can be modeled as a glass-like cylinder, like this, the animal fur has very complex internal structures inside. There's cuticle outside and cortex inside, which contains pigments that absorbs light, and the medulla in the center, which scatters light. So if we simply stop here, modeling the inner structures as participating media for each animal fur fiber, theoretically we can trace rays inside. But good luck getting a converged result. So what I did back then was to define a double cylinder model, and I added 2 lobes when the light goes through the medulla or the inner cylinder. When the light hits a fur fiber, the model is used to shade, and the light never needs to get inside the fur fiber. Okay. Therefore, in order to achieve good performance, we need not only digging into the micro world in a top-down manner, but also bottom-up abstraction or summarization after that. Another example, let's take a look back at the sponge cake model again. Okay. So if you remember, the derivation we just talked about is for single scattering. Of course, the analytic mathematical derivation for single scattering is already a bottom-up summarization. But I want to ask, how about multiple bounces? Do we have to perform multiple integrations and enumerate all possible scattering positions for every bounce? And theoretically, we can, but it may not be necessary. If we compare the single scattering results on the left with the multiple scattering results on the right, we can find that they look similar, and multiple bounce results just seem brighter and a bit different. This observation inspires us to tabulate our results. How? With the parameters of each layer defined, we can path trace it to acquire the actual multiple scattered BRDF lobe. Then we can simply fit this multiple scattered lobe with the parameters as if it is a single scattered lobe. Therefore, we end up with a huge dimensional table with infinite pairs of mapping from material parameters to single scattering parameters. Therefore, we can simply use a lightweight MLP to compress it. Speaking of neural networks, they are good at compression, but in the sponge cake model, we still perform path tracing to simulate the multiple scatter results, as we just mentioned. So we ask, is it also possible for a neural network to speed up computation, for example, layering 2 BSDFs into a new one? If we can do that, we're essentially introducing some neural algebra. In this neural algebra, BSDFs can be compressed into latent vectors, and we call them neural operands. And a small neural network can take 2 latent vectors in and output a new one as a neural operator. And in our specific case, the neural operator is essentially taking over the complex layering computation. Let's take a look at the results. Every point on this globe has 2 latent vectors representing the BSDFs of the top and bottom layers, and we use a lightweight neural network to layer them. It's pretty handy to be inferred per point, and the result is also noise-free, which is another advantage using neural networks to compute, unlike the traditional position-free path tracing methods. So I've talked about the performance challenges in appearance. Before we move on to the geometry, I would like to say that appearance and geometry issues are essentially the same. It's just the light transport inside certain materials or inside the entire scene. And they are even intertwined. For example, if we ask why photorealistic rendering is slow, based on our previous analysis, we know that it's because accurate appearance is often involved with complex geometry. For example, the porous structure inside a bread. And in the beginning, we just mentioned what is rendering. So rendering is the process that turns geometry into an image. Therefore, I would like to claim the rendering performance is bounded by the complexity of the geometry. Because the rendering process at least has to see all the geometry. If the geometry has a complexity of, for example, n, the rendering performance would be at least On. And I have an example to support this. Here's an early work of mine from 2014. It uses an extremely high-resolution normal map to specify every microfacet's orientation on the snail's shell. Each microfacet is purely specular. That's why we see the glints. And here's a zoom sequence. It demonstrates that even within a pixel, there are thousands of tiny highlights. Regardless of any possible acceleration methods we can possibly propose, in the end, we need to find all the highlights in a pixel to get a converged, noise-free image. And this observation tells us it's possible that the only way to improve the rendering performance is to decrease the complexity of the geometry or downsampling it. But we have one condition. We need the downsampled geometry to produce, ideally, the same appearance as before. That means we cannot just throw away the geometry that we cannot see, because if we do so, we immediately go from this vivid photo of a brown bear to an old-fashioned cartoon. So what should we do then? I actually like this example personally. Suppose you're driving in the night. You may notice the small patches around the lanes that are very bright. Why is that? Of course, there are some retro-reflective paintings, but some other designs have this kind of zigzag-shaped microsurfaces. Why is it good? Because in this way, for each incident ray, after bouncing twice, it will be redirected back to its original incident direction. That's why you can find it very bright in the night. But if we do mesh simplification blindlessly, without considering the appearance, what will happen? The result will be a plane. No matter if you do normal map filtering or not, it's no longer behaving like before. So I would like to say that the geometry simplification is no longer a standalone topic today. Simplifying of the geometry must come at the cost of complexifying the appearance. Whatever geometry we want to simplify, we need to aggregate their optical behavior together, both individually and between the geometric primitives. In some cases, for example, triangle mesh combined with diffuse or rough glossy materials, aggregating the appearance may not be an issue even if you don't do anything, just like the masterpiece work of Nanite. But in some cases, this will fail if you don't do anything about the appearance. For example, I've been playing Ratchet and Clank, and I was astonished that the per strand hair or fur works so well already in video games, although the number of fur fibers cannot be too high, am I right? But what if multiple or hundreds of furry animals appear in the screen at the same time? A simple trick, as you can think of, is to just create fewer and thicker strands when the animal is far away. It makes perfect sense. But when actually applied, as you can see from the bottom left and bottom right corners, the appearance seems too hard, and the color is not matching the middle, which is the reference. Since we have analyzed earlier, we know the reason already, right? With this simplification, each fiber now is representing a bunch, maybe 100 original fibers together. The geometry is simplified, but the appearance is not complexified. It's still using the previous model for individual fibers, which is wrong. So what we did is to simulate the aggregated appearance. We first generate multiple fur fibers in a thick cylinder, then start tracing a beam from behind. Let the light scatter inside, and we record the outgoing radiance. Then we can compare the individual fibers' appearance, which is the middle column, against the aggregated appearance on the right. What we can see is that they're generally similar, right? The aggregated appearance is inheriting the individual's appearance to some extent, maybe just dimmer. And it adds a few more lobes, like the big diffusive looking and the top and bottom lobes. So with this experiment, we tried to derive the aggregated fur appearance physically and mathematically, still considering a ray going into a volume of fibers. However, we failed. And that was the first time we realized how difficult traditional volumes, such as microflakes, aren't able to represent real, especially structured geometry. And this is also known as the correlation problem. I will talk about it next. But as a workaround, we thought of our tabulated solution. Still, we just need parameter conversion from individual fibers' appearance together with the statistics, for example, how many fibers will be aggregated together, their density, etc., all the way to the parameters of our aggregated model. Again, we can create the data pairs, train an extremely lightweight MLP. As you can see, only 2 internal layers. Then we immediately have our aggregated model. And based on the view distance, we also come up with the dynamic simplification scheme. So the number of fur fibers will be determined dynamically based on view distance. And also, we infer the neural network once, as long as there's a ray intersection. But still, the inference time only takes up 2% of our total rendering time. So the neural network is indeed simplifying the computation. Okay. You may argue that the difficulty may be from the curves as the geometry primitives. Actually, no. In fact, I have been looking at different representations that may be good at geometry downsampling and appearance aggregation, but there's still no luck for me. For example, the triangles are simple, but they can form complex topology, like the grassland. In this case, it's not easy to find a simple downsampling scheme. Voxelization is a good way to enable level of detail by dynamically selecting the voxel size to be comparable to a pixels. This can also speed up rendering and minimize aliasing, but is voxelization almighty? And the short answer is no. I spent like 1 year to identify 2 big issues on that. The first issue is about the appearance. A voxel is essentially a box, not a point. The light can come into any position from any direction to the box and can go out from any other direction and any other position. This is very much similar to the concept of a BSS-RDF. Therefore, the aggregated appearance of a voxel should be 8D. So how can we quickly perform the aggregation? And how do we store the 8D appearance? And if that's difficult, how can we support dynamic scenes and editable materials? There is one way to simplify the first problem. That is to assume that whenever I use a voxel, it is small enough so the positions inside a voxel can be safely ignored, or we don't distinguish them. This is essentially saying that we don't want a BSS-RDF, we don't want 8D, but instead we want 4D, right? But this will also make a voxel look like a uniform inside with some transparency, maybe directionally dependent. Then in this case, the second problem comes, known as the correlation. Just look at this image. There are 3 opaque surfaces, C1, C2, and C3. When we look from left to right, the voxel containing C1 has a transparency of 50% because the upper part will be blocked. And it's the same for C2. But together, if we have played with Adobe Photoshop, right? So we know that 50% transparency on top of the 50% transparency gives us 25% transparency, which means that we should still be able to see anything behind that, which is C3, this block. However, in reality, you can immediately tell me that C1, C2, together, they will block the light for all. And what's more complex is that if we move C2 up, and that means 50% through the voxel of C1, and also 50% for C2, but together C1, C2, if C2 is moved up, will still give us 50% transparency. Therefore, it is a very difficult problem of the positional correlation because recording the correlation, as we just analyzed, is indeed keeping all the geometry, which is contradictory to the reason why we need a voxel grid. But why the NeRF is successful then? Well, my personal understanding is that a neural network has the ability to distribute its computational power to the places that are most in need. Therefore, we may assume that the NeRF has virtually infinite resolution, so it's able to represent surfaces well. This is one reason. But getting back to appearance, since NeRF has the light and appearance baked into its representation, it's actually a light field, or sometimes we say a light source. Decoupling these components is another story. It's not yet sure how good they can be. Since I don't have a clue finding good representations for both geometry and appearance, I gave up. And trust me, it feels great. What I'm looking for next is whether I can find a good geometry representation that can help to accelerate ray tracing only, without considering any appearance. Why is that? Because hardware ray tracing is not pervasively available, especially on mobile devices. And distance functions are good alternatives, but they require sphere tracking, or in general, iterations, to move a ray forward. And most importantly, to build a small distance field of, for example, resolution of 64 cubic, it may already take more than 3 milliseconds. So we seek a good solution that is fast in both building and tracing, so it can support dynamic scenes. We come up with a method called ray-aligned occupancy map array, or ROMA, to achieve this. As you can see, it builds 3 times faster and traces twice as fast as distance fields. This is a new work that will be presented tomorrow in EGSR. So in fact, we plan to try both EGSR and HPG deadlines, but unfortunately, we made it before the EGSR deadline. That's the reason. So I'll just very quickly go over it. The highest level idea is that an occupancy map, or bit brick by the industrial friends, is a binary 3D volume that can be easily created using rasterization and stored using a 2D texture, where each texel is a 64-bit or 128-bit number. But tracing a ray in an occupancy map is still slow, because we still cannot afford iterations moving the ray in a DDA style. But there's only one case when the tracing is very efficient. That is, the ray is traveling right along the depth of one texel. And in this case, ray tracing can be done in O1 using some bit operations. This inspires us, is it possible to create all differently rotated versions of an occupancy map beforehand? So whenever a ray is given, we can always find the occupancy map where the ray goes straight inside a texel. Of course, this is impossible. But Instead of generating all rotated versions, we can create an array of limited numbers of rotations. So in this case, given an array, we can find the closest rotated direction and snap it to that direction to perform fast and approximate ray tracing just inside one texel. And to get the different rotated versions, no more rasterization is needed. We just need a computing pass to copy-paste the base occupancy map, what we call BOM, into a ROMA. Okay. The spatial resolution of the occupancy map and the number of rotations, which we call the angular resolution, can both be adjusted to trade between quality and speed. And the errors introduced by snapping the rays will be amortized over time with spatial temporal denoising. And we can also choose not to snap the rays if accuracy is the top concern. That's it. And as you can see, our ROMA works pretty well. And we also joked that ROMA wasn't built in a day, but in less than 1 millisecond. Okay. I like this robot. Okay. All right. So that's about my tentative explorations, resolving the performance challenges by appearance and geometry. There are a few random thoughts that I want to share with you. The first one is that, are the details really important to be modeled and studied? So if we look at these two images, I bet it'll take you at least 1 second to figure out that these are not mountains, especially for the right one, but actually the top of 2 wooden stakes. But they are really similar to the actual mountains. So how come that studying the details is crazy, but studying massive scale rendering is good, right? I would say small or large is relative. And the problems and even solutions in different scales may be connected and shared. The other thing I would like to share is that decades ago, when people are talking about photorealistic rendering, that's just about offline rendering. However, I think real-time rendering is undergoing a revolution. And I personally believe that aside from the improvement of computational power and hardware to do ray tracing, the most important technique is the spatial temporal reuse, and actually temporal reuse. With temporal reuse, appearance models are allowed to introduce quite a bit of noise, and also the same for the light transport. And the geometries can also be sampled and combined. This is previously anti-aliasing, especially TAA, and nowadays generally known as spatial supersampling, increasing the rendered spatial resolution, although using temporal information. So maybe someday, there's no need to deal with all the aggregation work. With some smart light transport methods, maybe we can really leave the ray tracing both between the objects and inside materials. About neural rendering, I've introduced a few projects of mine that uses neural networks. They can be counted as neural rendering, but more precisely, I'd rather call them neural-aided rendering, just like computer-aided design, or CAD. This is because I am still in control of the rendering process. I use neural networks to solve sub-problems that are either difficult or slow, and I do not expect neural networks to take over. In that sense, I share the same feeling with the presenters this morning. To combine neural-aided rendering with high performance, one must care about the lightweight use of neural networks, its efficient implementation, etc. As for reliable outputs, my understanding is that end-to-end solutions are often prone to errors because the output is directly shown to the users. That's why I was saying maybe focusing on a sub-problem would be better because subsequent rendering process may perfectly hide potential issues. This is very similar to the final gathering process in the photo mapping method, right? But still, in order to accurately actually benefit performance, the inference of a neural network, either synchronized or running per thread, need to be performed even faster. Systems that allow writing neural network inference in shaders would be greatly appreciated. And the same applies to domain-specific languages and graphics hardware. The other thing I want to talk about is just photorealism itself, rather than performance in 2D. It used to be not so hard historically. The painters in the age of Renaissance have already proved it. And nowadays, the artists have not degenerated at all, as you can see from the pictures and this unfinished one. And I found this stunning graphics online. Let's take a look. So as you can see, the artist is adding more details to the drawing. And it's getting more and more realistic. But we cannot help wondering why in 3D the photorealistic rendering is so difficult, right? All right. Okay. So if we take a look at today's animation and video game, I think they're pretty good, right? So the Super Mario Bros. Movie and Diablo 4, that's good. And if we go back to 5 years ago, the graphics was still pretty good, as you can tell from the Coco movie and the game God of War. And another 5 years ago, that was still pretty good, looking at the Wreck-It Ralph and The Last of Us. And actually, I couldn't believe my eyes. I made sure that the image of The Last of Us is indeed from the 2013 version of it, rather than the recent remake. So that was really stunning, right? So what can we conclude? So there's no fundamental progress over the last 10 years. Okay. So on the contrary, I believe that we have made significant progress challenging the most difficult rendering problems, for example, the real-time global illumination. And we're now, unfortunately, in the uncanny valley, trying to get from 90% realism to 100% of realism. But this is difficult, right? It's like taking an exam. If you work hard, it's easy for you to get from 60 to 80, but getting from 90 to 100 is very difficult. But I still think it's promising. When we look at the demo enemies by Unity, we still cannot say that this is 100% accurate, but we're getting there. Okay. By the way, I really like the coincidence if you look at the subtitle of this specific frame that I took from this video and combined with the title I typed over there. You see, rendering today is given only those who dare. Okay. And is there anything that we can work on right now? Of course. At least I can say anything related to human is still problematic. For example, the accurate look of the eyes and the multiple scattering from hair and the peach fuzz layer on our skin that actually creates sheen and softens the boundary, and the skin itself, both its reflection and its subsurface scattering, and the makeup that is not only on the surface of the skin, but maybe in it, and the cloth that I've been working on, etc. So these are all difficult problems to accurate appearance, and that's just for human. And I actually think we still have time, so I can talk a little bit more. So the other thing I would like to share is actually already out of my area of expertise, but it's very interesting. Why? Let's take a look at the two different curves in this uncanny valley graph. Okay? So if you cannot read that clearly, I can do that for you. So the solid line curve, that is actually for still objects. And the dashed line objects curve is for moving objects. So from intuition, I actually guess maybe when the things are moving, I will focus less on its rendered realism. But if you look at these two curves, you can find that it's on the contrary. Moving objects is actually magnifying people's feelings, right? So this means that not only physically based rendering, physically based animation is also needed. And I'm not talking about the simulation although they are often put together, but actually the photorealistic animation. And if you look at Siren, that was several years ago, you can still find it's rather unnatural for the movement, especially of the mouth and the muscles on the face, right? And I don't think it's completely solved with today's mocap technology. It still requires artists' work. So finally, the last question, are we good enough? My answer is that it's never good enough, especially if we want to climb out of the uncanny valley. And I myself certainly cannot represent the rendering academia, but my understanding is that even if there are smart tricks or hacks that can work perfectly, and even if there's AIGC, and in several years or decades may help us completely skip the analyzing process, we call ourselves scientists, so-called, okay? So I would often ask why behind all these solutions. And in this process, I think I've been enjoying it. Okay, so that's my understanding, and that concludes my talk. Thank you.
Thank you very much for this wonderful presentation. We have plenty of time for questions, so whoever wants this thing, please raise your hand. There you go.
Hi, thank you for the excellent talk.
Thank
it was very insightful. I was wondering if maybe you could go into a little bit more detail about ROMA and how it worked. You talked about capturing one rasterization and then rotating it, but I'm quite not sure I understood how that could work.
Okay, so let me go back to the ROMA page. I think this one can, explain it better. So first, thank you for your question. And so here's how it works. So we perform rasterization of an object. So this object will be broken into different fragments, right? And these fragments, based on their position, we can calculate where it falls in the occupancy map. So this is classic method. So we will have the base occupancy map, or BOM. And the second stage is that we create a big texture. And for the texture, we start a compute shader, or basically just CUDA. So to work individually on each texel. And, and we assume that this texture is an array that you can see something like this. Okay? So based on the texel ID, you can immediately know which view it belongs to, and where it stands in that view. And for each view, it's associated with a random direction, and that can be different per frame. But if we know that direction, and from the second step for every texel, and we can just trace, write every bit of that texel step by step. And when we are moving along the texel inside this ROMA, and it's actually moving in another direction on the BOM based on its rotation. And so we do this reading from BOM and writing on ROMA, and there's no conflict of writing, so that's why this step is fast. So once you have this array, you will be able to use that, and you're given an array, and you can find the closest direction where that direction is rotated, like towards the depth of the texel on this ROMA, and you can guarantee that these two directions are close enough, so you can do the snapping or not. Actually, even if you don't do that, I think the performance is still good. Like it will be converging like 5 to 8 steps based on our experiment. So yeah, I think that's a little bit detail that I can remember. Yeah, but still, if you want to learn more, so I think tomorrow's talk will be better. Okay. All right. Thank you.
Thank you.
Yeah.
There's another question right behind you.
Is this on? Yeah. First of all, excellent presentation.
Thank you.
Really enjoyed it. One question to the neural methods, and you mentioned that animation is so important there. Have you any thoughts? I'm wondering whether you have any insight on how to deal with neural methods and, let's say, changing geometry, right? How would you kind of integrate and combine that?
Okay, thank you for your question. And to repeat, and if I'm understanding it correctly, so when the geometry is changing, how can we still use the neural method to maybe capture its shape or like correlated or related appearance, right? Something like that. So I would like to say, previously, I don't trust in this until I read the paper of neural radiance caching, because that paper demonstrates that with actually quite a bit of engineering work, it is possible for the neural network to dynamically learn something with very limited budget of the time and very limited data. So if it can happen, for example, if you want to learn I know this is impossible just conceptually, okay? So if you want to learn the SDF of a morphable object, and whenever it changes the value of the SDF, you feed the new data to the neural network, and if it can actually learn that data and try to combine with the previous data learned already and give you a rather clean result, and that should be great. On the other hand, I haven't heard about any other cases where it is successfully trained online for the neural networks. So be cautious about that. That's basically my understanding. Thank you.
Thank you.
There's a question over there.
Oh.
So just carrying on about the neural rendering. So you say neural networks should be used to solve specific tasks so that you maintain control.
Yeah.
But you also say they should be lightweight. Is that important from an algorithmic point of view, or is it just because you're bottlenecked by the way GPUs currently work?
Okay. Thank you for your question. So if I understand correctly, that's it's about why do I need a neural network to let's see.
If you could use heavier weight neural networks, because a GPU could accelerate it.
So the sub-problems, right? So that's what you mean. So why I care about sub-problems?
No, I sort of agree that breaking it down to sub-problems is the right thing to do. I just wondered why the neural network that's solving the sub-problem needs to be lightweight. Is that just because you're bottlenecked by current technology?
Okay, thank you. I believe that's the same thing. So it's not always that the neural network need to be lightweight, but if it needs to be inferred per thread, for example, so when we're doing shading, so we definitely need to shade a point using or through a neural network, and it has to be inferred simultaneously and maybe not synchronized on the GPU. So I don't think it's very friendly to the GPU's architecture. This is one thing. And on the other hand, if we are talking about a neural network that is not so lightweight, if it is big, but if it's operating on the entire image, and I think if it needs to be inferred like once per frame, I think we can still afford that. So it is based on the different tasks. I should make this clear. So yeah, thank you. Okay.
More questions? This thing appears to be working again.
Nice talk. Concerning Uncanny Valley, I remember Markus Gross, Professor Gross, speaking that we are in Uncanny Valley like 10 to 15 years ago. So, so actually, I think it's very, let's say, subjective, and some people already can think that perhaps we are already out of, or that we are at least going, not down, but going up. So, and ordinary people are, I think, sometimes they don't believe it was rendered. It's so subjective. So for you,
yes.
What's the estimate when we will get out of the of the valley?
Yeah. Thank you for this comment. I actually share the same feeling. I mean, it's been a while since I sit down and enjoy a movie, because when I'm looking at a movie, I can't help figuring out, okay, what is still bad, what can be improved, something like that. So yeah, maybe working on rendering has the ability to raise the bar of aesthetics, which is good, right? So if I have a certain higher bar in terms of realism, I would say today's rendering is still not good enough. But yeah, I mean, there are artists who are really picky about this result, and there are like ordinary users who thinks maybe like the graphics from 15 years ago, that's good enough. And that actually depends on the on different people's own opinions, as you mentioned, subjective, right? Yeah, so I totally agree with this. Yeah, but on the other hand, if I consider myself a scientist, if I still think something needs a little bit of improvement, that's yeah, what I should work on. Yeah, thank you.
Maybe I'll follow up here with another question. You have focused a lot on ultimate realism, or like a very high degree of quality, but ultimately we are making tools for artists. So what are your thoughts on the impact of graphics research and rendering research specifically on artist productivity?
Okay, thank you for your question. So yeah, I mean, this is a question about how to connect the scientific findings with the ease to use property from the artists, if I understand correctly, right? So yeah, we do need this kind of artist-friendly design to, for example, translate the physical-based parameters into those parameters that are more intuitive. For example, the shininess is a typical like interpretation, which is often replaced by the roughness here in the academia, right? So I think that's one successful case, and I believe some work to connect the developers and artists, that's very important. And I don't see a problem like pursuing the ultra realism, and I don't see if that'll, for example, introduce more parameters that is really hard to control. Yeah, at least for now, yeah. So I think it's still good. Thank you.
Makes sense. Thanks.
Okay.
We still have a few minutes, so yeah, there's a question. Okay, maybe we'll need.
Oh.
That only half the thing flew. I'll just give you the other microphone.
I fixed it.
Okay.
Great talk. And do you think that AI will be the solution to solve the uncanny valley problem, especially for animations?
Okay, thank you. Thank you for your question. So will AI be the ultimate solution for us to jump out of the uncanny valley? So I'm actually cautious about this because on one hand, I have seen the possibilities and potentials brought by, for example, AIGC, its success on the 2D content creation. And I also see some successful applications try to, for example, generate the 3D contents and maybe even the NERF contents in different ways using the AI. So I assume people are still exploring different ways and see if it can actually work to get the 3D content. But I have actually two questions about that. One is that, do we really need 3D contents? With 3D contents, we have the geometry, we have the lighting, we have the materials, and inevitably, we have to combine them using what we know, which is the rendering equation, which is also wrong, which is also not able to create the, wrong in the sense of wave optics research as I did, okay? I should provide more context. Yeah, okay, so, but we do know that as a rendering researcher, I'm not content with the rendered realism yet. So as long as the generated content is in 3D, I can say it's unlikely to be photorealistic, at least for now. So the other question arises, right? So what would be a good representation as I've been trying to explore? So these traditional methods, the voxels, the triangles, including NERF, they have their own pros and cons. So if AI wants to do better, I think maybe AI should also explore some better forms to represent all these kind of geometry and appearance, and I believe that's the right way. So going back, so this is one thing I have seen its potential, and the other thing, on the other hand, I am still keeping an eye on it. I hope there's a success, and yeah, but I also wouldn't 100% rely on that. That's my personal opinion. Thank you.
Thanks.
Okay, last call. Any more questions? Apparently not. In that case, I think Elmar has a few more things to say about the upcoming boat tour. So,
thank you. Yeah, this concerns not only the boat tour, but also the event tonight. And I took notes so that I will not forget anything. So the place is called Blue Lagoon. We already mentioned this in the first session, but I wanted to repeat it once more in case people get lost. We also have the information in the program on the webpage. If you just go to the program, underneath the event tonight, you have a full description of how to get there. Basically, you take the tram 1 in direction of Scheveningen, and you get off at Scheveningse Slag, Belde aan Zee. It's all written on the webpage, so you'll know when to get off. So you can either take a Dutch along in order to help you, or you take also a sweater along, because unfortunately it might rain a little bit. Maybe it's actually good for the plants, but we will see. There is space inside, so we'll not get wet if we don't want to, but maybe it's actually nice to be a little bit cooled off. As you will know, there's 2 hours before we actually start with the event, because there will be drinks first, and at 8 there's only the dinner. This is because part of you is going to go on a boat trip in the meantime. We have our student, Matthijs Molenaar, who you can trust and follow to the boat, and he will then show you how you get on the boat, and the captain will show you how to get off the boat, because we have a deal that they bring you very close to the train station so that you can basically directly hop onto this tram in the direction of Scheveningen to be on time for the event. Did I forget anything? Yes, tomorrow morning, we already mentioned this before, we are not going to be here, because we are going to mingle with the folks of EGSR, so which means that our size will again increase a little bit more. And therefore we had to move to the big tower that you walk by every morning in the lecture hall, Ampere, but that is easy to find. It's on the ground floor and there are signs everywhere. So with this, I hope that you will enjoy the evening. Oh yeah, and I forgot, if you don't have one for the tram, you need a ticket. We have bought them for you. If you didn't get one yet, please walk up to Ricardo and he will hand it over to you. With this, enjoy the evening, and we see each other tomorrow latest, if you don't come to the event, but I think you will, in the AV Tower. See you then. Thanks.